how do we make sure that we actually have dependability and assurance? Going through the dictionary definitions, we've sort of come up with this one, which is, dependability is ensuring a specific system property is there, and also make sure that the analysis, engineering, and argumentation is there to support that is dependable. And from an assurance perspective, you want to have the confidence that it will work as expected and the qualities are there. And that, this is going to include a lot of different dimensions. It's going to be including the creation, exchange, review of the arguments and evidence used to convey that confidence. So that's roughly the definitions we're coming up with right now. If people feel like they want to, add to that, by all means into the chat channels, feel free to keep a discussion going on that. But that's what we're going to use as a working premise for this conference today. I
wanted to add one word to that, right? Especially, it's kind of difficult to say what this microconference is about, right? But and I know people are going to come. Well, I have an interest in the safety of the system. Other can come. I'm interested in the security of the system. But when we're talking at the Plumbers conference about the Linux kernel, these two terms are very difficult to actually interpret, right? So in the end, it usually boils down to integrity or confidentiality or availability of the kernel. And that is not at least directly related to safety or security or even contradicting to that, right? So that's why for the kernel, it's really a kind of a strange thing to say the kernel is safe or the kernel is secure, right? You're probably talking about either I've ensured integrity of a certain function or I've ensured confidentiality while using that functionality. And that's, I think, the better terminology to use. The other thing is the question of assurance, right? I mean, it's one thing to say, well, Case told me that seccomp works. It's another thing to actually have evidences that we know that we can argue that are complete, that we know that multiple people have looked at, and that we know that we'll still understand in 15 years from now, right? And all the question on how do I gather such evidences, and how do I present such evidences, and how do I present such an argumentation is all about assurance. And that's quite a large field as well. We're going to see a few presentations that try to present that in a structured way, and that's already the first step to call it an evidence.
Okay, so I'm going to move to the next slide then, I think, because you sort of covered this one now, Lucas. Okay, and so I think you want to continue to talk about this because this is your idea and we like it a lot.
Yeah, so I try to map out what I read in the abstracts, and I tried to figure out, okay, what are the main contributions? What are the main focal areas that the different presentations will touch on? And I found out that there's some topics about verification, some are about integrity, some are about fault detection and control, some are about argumentation completeness, and some are about development process. And when you what you find out is that the different presentations touch on kind of two of those areas. I mean, they can also touch on 3 or 4 of them, but I picked out the 2 main areas that I identified, right? So if we take understanding Linux lists, this is probably a presentation that's going to present a verification method to show that the Linux kernel has a certain integrity. If we pick out Shua's talk for Linux kernel dependability, she's thinking about how do I show the completeness of my argumentation with respect to development process. And similarly, you can map all the other talks as well into kind of these areas. So you're seeing that we're addressing various aspects in actually this mini conf here, and hopefully after all the presentations, it becomes more clear how this fits into a larger picture.
Indeed. And those obviously other talks and other sessions are very much related into this, but we wanted to start to gather everyone together and start to talk about this area as a specific set of considerations so that we can start to build up a common understanding in this area. Shua, did you want to say anything further on this?
Yes, a couple of things. One, this is a great opportunity, at least for me. I found that we can bring together the aspects of work that's happening in the kernel space, right? Case is working on security, looking at the security aspects, and we are bringing in safety into it and looking at how they both intersect. Or there are lots of commonalities and a few maybe differences. So threading the story together for the entire kernel space, looking at it as a dependability aspect as opposed to just focusing on security or safety. And because at the end of the day, having a secure and safe system makes it dependable, that we can have a dependable systems.
Excellent. Well, and so I think with that, what we will do is we will once again welcome everyone, and we'll turn it over now to our first speaker. So with that, let me just share it over to Julia, I believe. And we will make you speaker, Julia, and let you start to present and share your slides. Yep, we can see you. Excellent. And it's loaded.
Okay, thank you. So this talk is about understanding Linux lists. It's joint work with my colleague Nick Vorlansky, and it's based on a paper which will appear at the end of September at the conference Automated Software Engineering. Basically, the goal of this work is to understand some kind of very low-level aspects, implementation patterns in Linux code, try to express them in a more high-level way. And as such, it's related to general understanding of the kernel code, which is important for dependability and assurance. So lists, everybody's familiar with them as a fundamental data structure. Anytime you have a bunch of things and you want to put them together, you can put them into a list. It's very often useful in an operating system kernel. We have requests that come from the user space, come from devices and so on. We collect that information. At some time in the future, we might want to iterate over that information, find that information, search for it, and so on. So lists are used all over the place in the Linux kernel. Lists are associated with three different main concepts. The most important one is obviously the elements. There's the values that are contained in the list. Another important element are the connectors. So that's how you get from one element to the next one. And finally, we need to be able to access our list. So we need some kind of head, some way to find the start of the list. So these are properties that are going to be common to all kinds of lists. So afterwards, the question is, how should we represent them? Basically, what type of data structure should we use to represent our lists? And so here we have a challenge because different types of lists contain different kinds of objects. So we have lists of work in work queues, we have lists of tasks in run queues, we have lists of maybe inodes and so on. But it would be desirable to have only one list type, and in particular only one set of list operations that's going to manage all of these lists. That will encourage people to use these API. If we can if people get familiar with the API, if it's useful in many situations, then they'll use it. People can understand the code and so on. So that's what's offered in Linux kernel today. We have a type which is called list head. This is a very simple type. It has two components. One of them is called next. It's going to point from one element of the list to the next one. And there's another component called prev. It will point from one element of the list to the previous one. So even though the type is very simple, it's actually giving us something quite powerful, which is a doubly linked list. So here's an example of these lists. So we see we have three of these structures. They're hooked together. We see the doubly linked list aspect. So that's all very good. But a quick amount of thought will show that actually something is missing. There's actually no elements in these lists. So this list, as I've shown it here, is actually not very useful. So the way these are actually used in practice is by embedding the list head structure into some other data structure. So here we have two examples of that. Hid dev, it has a list head field which is called list, and hid dev list, it has a list head field called node. And now that we have these more complicated types, now we can create a more interesting list. So here we have a list, and its head is here. This is going to be the starting point of the list. It's not actually an interesting element of the list. It's just showing how you get to the list. And then we have these different elements, hid dev list, and then these are connected to each other. And then as we're following this connection path, then we can use the function or the macro list entry. And list entry is a macro is implemented using container of. It will get us from these list, next, and prev fields back to the enclosing information of the data structure, which is actually what contains the information that we're looking for. So that's the basic idea of lists. What this is giving us, we have one data type, and thus we have one API that can work for all different kinds of lists. This API, it's got a moderate number of functions. You can add elements to a list. You can add elements at the end of the list. We've seen list entry, which gets us from these list head pointers out to the actual data. And it also has a large number of fairly friendly iterators that allow us to iterate over lists. That's kind of what you want to do with lists, and get different pieces of interact with them in different ways. And so this is some other benefits. Having the list connectors embedded in the data structure improves locality. If we're actually interested in data which is right next to the list prev and next fields. And the list operators such as list add and list add tail, they embed some occurrences of read once, write once, and so on that gives some concurrency guarantees. So the person using the list doesn't have to think about all of those issues. And so we can see that this is how these have been sort of approved by the Linux kernel community. These lists, they were introduced in 1998 or maybe 1997. At that time, there were just a bunch of different ad hoc implementations of lists in different parts of the Linux kernel. And then this one was introduced, then it sort of gradually took off being, first it was used in file systems, and then it was used in other parts of the kernel. Sometimes it was people actively translated existing code to use these kind of lists. Sometimes these kind of lists appeared with new code. And as we can see over time, the number of uses of these lists have steadily increased. So we can see that in general it's a success. On the other hand, there's some problems with this situation. The main problem is that we have just one type, and we have, as we've already seen in our example, we have the list head type everywhere. So if you see a list head, you know it has something to do with list, but you don't really know what's going on. You don't know what is the role of this object that you're looking at. Is it the head of a list or is it connecting a list? We actually using the same type for both of those purposes. And if you figure out that it's the head of a list, then you don't have any information about what the elements are. It's just a list head type. It doesn't point in any way to where the element values. And likewise, if we have a type and we realize that this is an element of a list and the list head structures are the connectors, we don't know what kind of list heads it can be reached from. So, and if we go back to our example, we have these two types here. I put them next to each other for being helpful in the presentation, but actually these two types are not even in the same file. And as I've indicated by the code, there's no comments associated with these types or anything like that. We just have the two types. They have some fields, and they both have fields called list head. We did actually do a study, and we found out that all of the fields called node actually are list elements. And so perhaps you could guess from looking at the definition of hid dev list that these are actually list elements. But that doesn't give any information about where these list elements are accessible from. We also studied the field name list, and we found that sometimes it's used for list head, sometimes it's used for list elements. So from just looking at the type, the hid dev type on the left, we don't actually have any information at all. And even if we figure out, again, whether it's a head or an element, we still don't see the connection between them. So as I mentioned, there are no comments. The structures are defined in different files. There's really nothing to show in the structure definitions to show the connection between them. Overall, we found that only about a third of the list head fields in the Linux kernel have comments. Depending on the version, we looked all the way from Linux 3.0 to Linux 5.6. And even when they have comments, sometimes the comments are useful. So it says like a certain field is the head of a waiting SRB list. So there we know that it's a list head and we know what the type of the elements are. And some of the comments are obscure or irrelevant anyway. They don't have anything to do with the list structure. It's just a comment there for some other purpose. So the actual list head fields are actually commented in a way that is going to give information about the structure is much lower. On the other hand, we can observe that if we can actually find uses of these lists, then we do get some information. So here's a small example, again, with our hid dev and hid dev list types. And the list head, if we have this list for each entry iterator, the list head is always represented in the second argument, and the list element connector is represented in some way by the first argument and the third argument. In this particular case, the first argument is actually the type of is a variable that represents is going to point to each element of the list. And so if you find the type of that variable, then you can find the type of the elements of the list. And the node field is the connectors between the lists. So if you can find this information, however, finding this information, if we start out with just the fact of hid dev list, for example, the hid dev list is because it's type information, it's separated from the actual use. We can't use grep very easily. The names list and node are very common. We can't also, it's another way we can't really use grep in a deterministic way to find the information we want. So the information is there, but it's not actually very easy to extract. And similarly, we have list add tail, which also provides the same kind of information. If we find the second argument of it is going to be the list head, and the first argument is the list head connector. So once we know these roles of these different arguments, once we figure out the types of the different values, then we can make the necessary connections. But in terms of a human looking through all the code, it's not very easy to figure out. The information is scattered in different files and functions, and as I've pointed out, it requires knowing C type information, which is not actually associated with the expressions that we're looking at. Having found this problem, we decided to make a tool that would basically automate the process that I have described in the previous slides. That is to scan the code base and collect information about the list operators and their arguments, and then make inferences from this information. So here we have the advantage that the API is moderate sized and it's very widely respected. There's very little code that actually interacts with the list in a low-level way. And so in that way, we're able to find out a lot of information. So basically, what we're trying to do is to find types of the form head and element. So they're going to be described in some terms, L1 and L2, and what we call list names. A list name might either be a structure type and a field name, or it might just be a variable. So it's probably easier to see this in a more concrete way. In our particular example, we have hid_dev.list. That's going to be the type of the list heads. And we have hid_dev_list.node, and that's going to be the type of the list elements. So that's something we're going to infer. And then we get a textual representation out we can provide to the user, and then the user can understand what these different fields represent and how they relate to each other. So in our results, we found over 10,000 list heads in Linux 5.6. We found some of them are not used with the standard operators, and so, or some of them appear not to be used at all. So there were about 10% for which we didn't find any information. But again, if we go back all the way from Linux 3.0 to Linux 5.6, in all of the versions, we can find around type information about around 90% of the list head of the declared list head structures. So for each case, we can figure out which ones are actually just pointers, heads of lists, and which are actually representing list elements and how they connect to each other. So here's some statistics for two versions that we considered in a bit more detail. You can see for 5.6, we have around 9,000 that we were able to type. 55% of them are only used as heads, and around 41% are only used as elements. And then the most interesting thing, of course, are the ones that are used as both heads and elements. And so that's the way you can do something more interesting than just make an ordinary list. And so we're going to look at those aspects in more detail. We also offer a visualization tool. It's based on GraphViz, so it lays out these boxes and circles and so on in a nice way. Basically, it takes the types and it finds all of the fields of a particular type. It puts them together in a box, and then it connects the ones that are heads to their elements. The ones that are heads are going to be blue, and the ones that are black are going to be the element type. So we can see our canonical example here. It's going to produce hid_dev. It has a field. It only shows the list head typed fields. We have the list field, which is the head of the list, and it points to elements of the hid_dev list type. Notice that here we have a file name because this is a type which is defined in a C file. So we consider that it's perhaps specific to that particular C file. And our list, the elements are going to be connected. Our hid_dev list elements are going to be connected by the node field. So this describes everything we need to know about the structure. Okay, so the next example I'm going to do, this is a very simple example. We have a more complex example here. It might be a little bit hard to see depending on how big your screen is, but this is the task struct structure, which is used by the scheduler to represent tasks. So task struct is here, and then you can see that the visualization tool collects transitively all the other lists that have somehow have a relationship to the type that you actually asked for. So it's a bit complicated, but you can see there's some interesting examples here. Some of these list heads, they have loops. So that means we have a head and the elements, and they all have the same type. And we have also, so this is probably the most interesting thing we have here, but there's lots of these looping things. So actually, in some kind of types, it's a common situation. And so we're going to look at some of them in more detail and try to figure out what they actually represent. Just some statistics. We saw before the number of these list head structures that are both used as both heads and elements. Sometimes they're just loops pointing to themselves, like we saw just now in task struct. And sometimes you have a head which points to an element type and an element type which points back to a head type, which we call a mutual pair. And then there's some other cases that are more complex, which I am not going to go into. So we'll look at some of these interesting examples. So we're going to start with thread group. So thread group The type information just says that thread group, that it's used as a list head because it's colored, and it's also pointing to elements that are also going to be they're also going to be task structures, and they're all going to be connected by their thread group fields. So basically what we have is something like this. We have all these task structures, and we have the thread group fields, and all of the task structures are connected to each other through their thread group fields. So this looks sort of like what we saw in the beginning. We just have these links going around. Actually, I didn't show the links going the other way to be a bit more simple. And so it's kind of hard to understand what's going on here, because normally we think of a list as having a beginning and then a bunch of elements. Whereas here, everybody's a thread group, everything's a task struct, everybody's connected to the thread group, so nothing is really distinguished between anything else. There are some actual constructions in the Linux kernel which really are like that. They're just a bunch of objects that have no particular hierarchical relationship between each other. They're all of the same type, they're all connected to each other. But in this particular case, that's not what's going on. Actually, as I've kind of hinted by moving one of them up here, one of these thread groups is the leader, and then the other one of these task structs is the leader, and then the other task structs are kind of are in its group. There's the followers here, the ones shown here. And so this is a structure which we call an umbrella. So an umbrella is going to be basically like a tree. It has height 1. And it turns out when you have an umbrella, there's always some other, or there's typically some other field in the structure, and those other fields are all going to point back to the leader, somehow the head of the list. Even if everything has the same type, still one of them is going to be designated as the head. And so you can see where the umbrella idea comes from. This is at least the right half of the umbrella. We have the top part, and it has the things going down here to the different elements. And so actually, even though these things have all the same type, they're going to be used in different ways in processing things from a list point of view. If you want to iterate over all of the elements of the list, you're only going to start here. If you're in one of these others, if they're not the leader, and so we don't do the iteration. And if we want to add new elements to the list, we will add them here, either afterwards or before, depending on which kind of addition is wanted. So they all have the same type, but they're used kind of in different ways. So going back to our task struct, we can see that we have some other of these self loops here. Here we have tasks, and this is also sort of an umbrella. It's kind of maybe a more implicit umbrella, because in this case, there's a single designated task which is global to the system, which is called a init task, which is then going to be kind of the leader for all the other tasks. And these tasks are also pointed to by some other variables, which is going to collect dead tasks or dying tasks in a temporary sort of way. But again, we have this umbrella concept, even if it's not implemented in exactly the same way. The next thing we're going to look at are trees. So that's going to turn out to be what this pattern here represents. So this intuitively, if you just look at the beginning, it looks like an ordinary list. We have the list head as shown by the thing being in color, and the list elements as shown by this thing being with a black background. So the idea from the p-traced field of the task structure, we can get to other task structures that are connected by their p-trace entry field. So we can see how that looks. So it looks as one might expect. We have our p-traced field, we have our p-trace entry, other task structures and their p-trace entry that are all connected to each other. But then we can remember that all of these things are task structures, and they all are going to have p-trace entry fields, and they're all going to have p-traced fields. So the real situation is something that looks like this. And this p-trace entry and these other fields can also be connected to other task structures. And so we end up with something like this in the more general case. And so now if you turn your head on the side, then you can see that each of these nodes is going to have 2 children. And so we have basically a binary tree. So the characteristic here of being a tree is that we have an ordinary list structure but both the head and the elements are within the same type, and that allows us to do the recursion that's necessary to build a tree. And then here on the side, we have another situation exactly like that. Here we have the head, and here we have the elements. But here we have the same self-loop kind of thing that we saw for thread group and tasks. So actually, this is an umbrella tree, a tree made out of umbrellas. And so basically, we have our siblings, which are going to be tasks. And normally, we add new siblings by going up to the parent and looking down at the children. So adding a new child to the list of children that the parent has. But sometimes there's a desire just to iterate over the siblings as they are without looking for the parent. And in that case, we use the same kind of leader as was used in the thread group case, the group leader, to differentiate the beginning of the list of siblings from the rest of the siblings. So the final example that we're going to look at is the idea of a ring. So this is what I mentioned previously. Sometimes we have one of these self loops, and it's really a loop. There's no distinguished leader. All of the elements are somehow equivalent to each other. And this is useful if you have a bunch of elements which are all having the same role. There's no need to have an artificial extra head if that's not useful for anything. But unfortunately, all of the iteration operators are designed for the case where we have a head that we're not actually interested in exploring. And then we have, we're going to iterate over the elements, and then when we get back to the head, then we stop exploring the element values. So if we have a ring where all of the values are actually important, we can't actually use it directly with one of these iterators. So then what's done here, the kind of common pattern is to artificially add a head element into the list. So we have list add tail. Remember, this is the list head. And so this is playing the role of a list element at this particular place. But then in the next step, we are going to iterate over the list. But now we're not using what we just considered the head on the line before. Now we're considering this variable head to be the head, because actually that doesn't contain any interesting information. And then we're actually able to iterate over all of the elements of the ring in a convenient way. And then once we're done with our iteration, then we can just delete the head, which is not useful anymore. So this is how it can be recognized in the code. It can also be recognized in the graphs by this this mutual pair aspect, because as I mentioned here, in one instruction we consider head to be an element and this thing here to be a head, and in the list for each entry we switch things around, and so that's how we get the two things that are pointing to each other. So a type system wouldn't be a type system if it wasn't at least helpful in finding some bugs as well. So really the main goal of this project is to help people when they find a list head field to actually understand what the role of that list head field is. But still it also enabled finding some things that we use in an inconsistent way. In particular, the main problem that we've found with these list objects is that since we have the same type for both the head and the element, and since some functions such as list add and list tail just take two arguments of that type, there's a tendency sometimes to use those arguments in the wrong order. And that also is another situation that can generate one of these mutual pairs. So we can look at how this plays out in the code. So here we have a list for each, and we have a list for each safe. In both of these, this argument, the last argument is the argument representing the head. So we see that the variable fighter clocks is going to be the head, and then the other argument is representing the elements. And then we come down to list add tail, and we can see that the arguments are used in the wrong order. The head is supposed to be the second argument, and clock error listed as an element is supposed to be the first argument. And this is quite a big problem because on the one hand, here what we're doing is we're adding a variable type list head to a list, and this variable isn't going to have the expected data that we have in most cases on the data that we expect on elements. And then the second problem is if this variable here is actually pointing already to some list of elements, adding it as an element to some other list actually is going to have the effect of cutting all of those edges, and all of that information will be lost. So in conclusion, we have developed a simple type system for lists that distinguishes between the heads and the elements. It helps people understand, or the goal is to help users understand what the different lists represent, how they're related to each other, what the structures are. It also, once you have the visualization tool, is very helpful for getting an overview. And we also provide a list, a textual representation of all of the places the list is used, so that it's easy for the person to go and try to understand in a deeper way what's actually going on. And then this raises a number of questions that could be investigated in the future. Are there other kinds of patterns that we could look for besides umbrellas, trees, and rings? Are there other C types that need higher level descriptions? So in this direction, we've already started looking a bit at container of, because container of takes one type and turns it into another type. It can often take generic types and turn them into more things that are more specific. We can wonder if these types that we have inferred should actually be enforced in some way. For example, to allow compiler to avoid this list argument swap bug that we found. And if the types are not enforced, is there some way we could actually systematically document, integrate this information into the documentation, the comments, or some other form of documentation, so that one could understand lists in a better way. So everything I've presented is all the tools, and all of the results are available at this website. Thank you.
Thank you very much, Julia. Does anyone have any questions? We've got about 3 minutes left, so there's enough for a little bit of a question.
Right.
Quick question, Julia. How do you see this as something that could go into kernel tool set, or is it going to stay outside on the GitLab?
So it depends whether people find it useful and so on. I mean, myself as somebody looking at kernel code, I would kind of like to just see the comments in the code, and then I would understand the lists, and then I would, we have some types where maybe the names hook up and stuff like that, but there's some other types, they have like 15 lists in them. And so then it starts to get quite hard to understand what is this one actually, especially when they have helpful names like list and node and element. Well, elements is at least something, but I don't know, it'd be good to at least encourage people to get some documentation into the code. I don't know if it has to actually be as part of the kernel. I don't know if the lists actually evolve enough to justify that it has to be in the kernel tree, but it depends on what is wanted as well.
So it could even be, if it stays outside, it could be a tool for somebody new trying to understand the lists and what's going on, can use it to get a feel for how these lists are being used by a particular driver or subsystem, or so on. Okay, great. Thank you.
And basically, as you saw in the example, you can give it one type, and then it will give you everything that's connected to, and then you can, with a big enough screen, you can kind of understand. Most of them are not that big, but some of them are very complicated. So,
very
Great.
cool, Julia. Thank you.
Thank you.
Yeah.
thank you.
Okay, and then with that, I think our next speaker is, feel free to say thank you and express your thoughts in the public chat here, or we also have associated with this microconference, there's a chat column on the side that will be recorded. There's also a rocket chat session, and I'll paste the link to there so we can continue discussions on certain topics after the presenters speak in the rocket chat as well, to keep the discussion going if you want. Our next speaker is Dr. Alana Kopperman and Ravi Dependability. They'll be talking about TCP safety. And so with that, I'm going to give presenters over to Alana. And Alana, if you want to unmute And I will unmute Ravi so he can participate as well. So you should be able to see the presenters now, Alana?
Still waiting for my presentation to come up.
You're going to need to go, since you're a presenter, you need to coordinate that on the plus sign on the bottom. Click on that.
I see.
And then you should be able to see a list of upload presentation. Scroll to your presentation, click on the circle, make it green, and then confirm it, and then your presentation should come up. I'm getting good at this.
Oh, where's that list of the presentations?
There's a plus sign at the very bottom.
Yeah, I see it says upload a presentation. I did that before.
Click,
So.
click on that, and that's where we can select from.
Ah, okay, I see. Okay. I don't see
Just
my
a second.
presentation.
I uploaded it earlier on, so I know it's there. Just scroll down, maybe. Oh, something come. It's there. It is now. You got it.
Oh, okay. Great. Okay. Hi, everybody. Sorry for the delay. The work here is a presentation by myself together with Rafael, I guess, Davidovich. Both of us work as safety architects at Mobileye/Intel and involved in designing solutions, safety critical systems. And we wanted to talk about today a brief introduction to a specific topic, which is I hope you see this properly, because by me it came out a little.
It's gotten a bit big.
Yeah. Okay. Anyway, whatever. But so I'll read it and I'll fill it in. It doesn't quite match the screen here. Okay. What this is about is we're using BASIB, which is a data structure. In about a minute, the next slide, I'll give a little more detail on that for people who don't want to know with it.
Yeah.
We're using this really as a use case, meaning what we're not trying to do is to zoom on CB for qualification or anything of that sort. We are trying to use the TCB to understand better. Oh, thanks for whoever aligned it. And I'm aware that it's a bit broken from yesterday's presentation, a bit of problem with my audio. Rafi will be taking over in a bit, and I hope his audio will be better. So bear with me and try to a bit fill in this. It worked yesterday. I hope it'll work.
It's mostly coming in.
Today.
We're following it enough, Elena.
Yeah, it's told yesterday.
Going.
Okay. Yeah.
Going.
But anyway, so this is basically a use case for us to try to analyze what types of data are available, what data is critical, and different software-based means which are available or can be to protect that data. Okay, and our goal is, as I said before, not so much to qualify the TCB in itself or to provide a complete safety analysis or to cover all of the failure modes, but to use this as a baseline to find different types, which exist perhaps in other data structures or other areas of the Linux kernel, how we should relate to each different types based on different failure modes and different mechanisms which we've been working on to try to help protect the different types of data available in different ways. Okay, so just in case anybody is familiar, just a very brief overview. The DCB itself is a very fundamental data structure, which a thread block. And for obvious reasons in safety critical systems, we have to ensure the safety, the integrity of the TCB, because otherwise that will lead to errors, and we won't be able to ensure safe thread life cycle management. That's why TCB, which is, we chose instead of the PCB, which is a much more complex data structure for analysis, we wanted to keep it down to size. So we focused on the TCB, A, because of its fundamental importance, and because it's a more manageable data structure for us. Okay, what important, okay, we have the wrong version of the here. Okay, we'll try to work with this. This is an older version. The TCB during when we're dealing with it, they have a variable life cycle, meaning that they exist in memory. Then they're at a certain point they will context switched, and then the TCB will get switched out of it, and at a later stage obviously will get switched back in. And context switch is a time when TCB is particularly vulnerable from a safety point of view. And when we analyzed the TCB, we identified various failure modes which are possible during the context switch. And we worked with 3 possible failures. Again, we are not claiming that this is a complete list or a complete analysis, but we worked with these 3 failure modes to where the data can be corrupted. There can be issues of what's called a wild pointer, with some kind of kernel bug, which cause some kind of memory write error that will cause corruption of the TCB data, and memory bit flips, which are based on errors. Based on these failure modes, we did an analysis, and we looked at the different data fields in the TCB, and then try to identify which data fields are safety critical, which are vulnerable to each of these different types of failure modes, and what action mechanisms we can define to ensure the safety of the data. Okay, I'll go on mute and let you take over from here. Apologize. After this call, you can download a more graphically, we made tables and made this legible and easy to understand, but I'll use this slide meanwhile.
Okay, well, you can, I just made Rafi a presenter now. So Rafi, if you want to take it away, and if you can, put the new slides maybe in the Rocket Chat link so people can get it while we're working. That might be a way of compensating too. And we'll upload them over here after the call. Rafi, can you?
Okay, yes.
Okay, good.
Can you hear me?
We can.
Yeah, okay, excellent. So, Ilana, can you
just
move
try.
the one?
Just go on to it and try. Your presenter now, Rafi. You should be able to advance it.
Okay.
Yep.
Okay. Okay, so basically what we did when we classify the data, we have several classes of which we try to classify the data by. Basically, the basic classification is if the data is safety critical or not, meaning if a corruption or a change, unintended change to this data will lead to a potential safety fault. So some fields are relevant for safety, some are not. For example, the tracing feeds or file system information may not be safety critical, while other data related to memory, task state, and so forth will be safety critical. In addition, there is also the kind of that the category of when is the data updatable, meaning TCP data may be updated during runtime, of course, but also there are some feeds in the TCP which are updated even when the thread is switched out. And this classification is important because it impacts the proposed mitigations. So this is something that that we did as part of this work. In the more updated presentation, so we have a table which we grouped the type of fields that you will see in the TCP. For example, we grouped it into categories like scheduling information, task state information, process credential, general, and so forth. For each one, we gave some examples and provided the classification of this group. So let me browse through this. Okay, about the mitigations. Again, in the updated FOIDs, this is a bit more organized, but let me start second with the possible failure modes. I think Ilana touched it earlier, but basically we identify for this work, we focus only on a limited set of failure modes. We don't have an intention to cover all the failure modes. So we're talking about corruption, whether by bit flip or wild pointer, and also failure to update the TCP when required. Regarding mitigation strategies, oh yes, now that's the one that's the updated one. Okay, so.
Oh, thank you.
So if you can go one foil. Yes, now I can. Okay, now I can do it myself. Excellent. Okay, so for mitigation strategies, first of all, as Ilana mentioned, we are suggesting here software-based mechanisms only for our mitigations, and we identified the two main vectors as the mitigation strategies. One is for detection, so that would be after the fault detection and taking the appropriate action. And another type is the prevention type of mechanisms, which will prevent the fault entirely from happening. Okay, here we have some examples of possible prevention type of mechanisms. So, for example, there are several existing kernel configurations which we can deploy and protect the TCP information. That would be usually configurations that prevent from writing to some areas or prevent some users from writing and things like that. Another method which we identified was to use memprotect to guard pages where TCP is stored. So that's obviously requires us to know or to group all the pages where TCP is stored at, and then apply some protection on these pages. So that's also true for the next mechanism, which is making it read-only. And here, for example, the classification of the data is important because you want to know which data can be written and when. And also you want to know if there is data that is not supposed to be changed at all, then you can make it read-only, for example. Another method is granting write access to TCP only via something like an hypervisor or something like that, which would mean that any write to this TCP that comes outside this hypervisor is basically illegal, and you can prevent it. So that's also one of the options. In the detection type of mechanisms, we have we thought about one proposed solution is doing like a CRC or a checksum on the safety critical data. And again, you have to be able to identify the exact conditions in which this data would be written when it is allowed, and only then apply this type of mechanism. And then when you try to use this data again, for example, you can do it when the thread is being switched out. And this is when the kernel saves all the TCP information. And then when it's switched back in, then you can check if there was any corruption during the tower change, during the time that the process was, or the thread was switched out. So that would be like a detection type of mechanism. And I think this brings us to the call for action. This one is yours, Ilana.
Okay, hi. So thank you, Rafi. With your action, well, how we would like to take here from here, and if anybody here in this group is interested in joining in this effort, even for this, I would say maybe to identify additional failure modes for data protection, but even within the context of TCP to complete the classification, the different safe mechanisms we've used in different specific ways, but to generalize that and to add additional kernel configurations which can be relevant, additional mechanisms which can be used for mitigation, and to use this as a general safety mechanism protecting safety critical data in various ways, and basically to establish a library of methodology safety mechanisms for data based on well-defined criteria and failure modes. Okay, so that's where we would like it to take it further to generalize from the localized work on specific areas to protect data and to turn that into a more general mechanism. Yeah, these mechanisms are more or less implemented, but again, in a local way in specific areas and not as a general safety mechanism. So we would like to take it further to have a general definition, classification of when they are relevant, how they can be used in a more general case. Okay. Okay, the current solutions are really in user space and in proprietary code, and we want to turn this into public and should be part of this kernel. Okay, that's really the next steps. There's nothing we can currently share, but that's where we would like to go. Okay, so that these should be safety mechanisms as part of the Linux kernel. Lucas, to answer your question.
What does it mean if you access the PCB, how can it be in proprietary code? I don't understand. You mean
I mean, basically we have user space.
So from user space, you just access the kernel memory.
I mean, if you go back to this configurations, there's a hypervisor which is not of the Linux kernel. It's not really code which is currently something that's the kernel, and that's where we would like to generalize. Okay.
Okay. Well,
as the next steps.
Thank you again, Ilan and Rafi. I'm afraid we're out of time right now. We're going to need to speak to the next, switch over to the next presenter. But thanks again for going through this. And again, if people want to have discussions, there's a chat here in this BBB system, as well as the Rocket Chat over in the other system. But we've got a channel there. So I'll put the channel in and we start the next person. So with that, our next presenter is Ben Dukes in Jens. So I'm going to switch the presentation over to Ben. And I'm going to unmute. And Jens, if you want to unmute, you should be able to speak too.
Yes, I think so. Can you hear me?
We can.
Good, perfect.
And if you want to turn your video on, you probably can do that too.
It doesn't work.
Oh, okay, fine. Well, then it's up to Ben
I'm
then.
just working this end.
It's up to Ben then. Good enough. And Ben's got his talk up, so I will just go back on to quiet mode. Take it away, Ben. And Jens. Oops. We can't hear Ben.
Ben is still in headphone only mode. He needs to switch.
Yeah, you're going to need to come back in speaker mode. Sorry, Ben. Jens, do you want to give everyone a little bit of an overview while we wait for Ben to rejoin?
Yeah, so what we did here is to look at issues involving machine state for a safety process. That is a process that is running on a Linux kernel, some sort of program consisting of one or more threads, and one of these threads is suspended for some reason to enter kernel mode, for an interrupt or whatever. There's, of course, a lot of the state is saved, the process or the thread execution state is saved. And what we looked at here specifically, how do you protect that state? You know, the state is stored in various data structures within the kernel. Of course, all the points that Ilana made in our previous or in the previous presentation apply here as well. So as long as data is being stored in kernel data structures of some sort, they are at risk of being corrupted while the thread is being interrupted for some reason. And so we looked at what can we do in order to protect that state, and that's what this presentation is about. So Ben, are you ready? You still, I think. He's now muted. He seems to be back.
Okay.
Yeah.
Great. Hopefully I'm now back.
You are.
Great.
Excellent.
Right,
Just
so
a second.
now
Let me make you back to being the presenter then. And you should be good now.
Great. Okay. Okay, and okay. Right, so I think Jens gave me a quick introduction. I'm going to skip over about myself and Jens. Obviously, Jens has got a lot more experience than us. So this is a project that CodeThink are currently doing under the Electrobit, under Electrobit's guidance, which is why myself and Jens are presenting this. So I'll do a quick introduction. So we're looking at very similar issues about interference to the CPU's core state for a system. And generally what we're looking at is an SIL 2-level system with mixed safe and non-safe processes that could be happening. Although we're still looking at a controlled system where you're not looking at arbitrary execution. So we're mainly looking at currently x86 as our example, which will be a little bit specific for our use case, but this has some general overviews for any system that with a complex modern processor. So we'll go through some of our fault analysis, go through the faults that could evolve and also be looking at a mitigation that CodeThink have been developing. So we'll go quickly through the CPU state. So modern systems have a lot of state, and we're going to sort of define a little bit of what we're talking about. So we're going to ignore things like bus bridges, interrupt controllers, and any other auxiliary processing that may be happening. We're going to assume that that is being protected by a different measure. So what we're going to talk about is the directly accessible register state that a compiler such as GCC may decide to use, or that's fairly easy to output code for, such as the accelerator registers. We're not going to really talk about the auxiliary control registers like the debug. They're really only available from the kernel and generally require specific coding. Although you could argue that some of these are part of the execution state that directly affects how your process is working. So, I mean, just to illustrate the problem we're having here, this is an x86 64-bit register state as from a Wikipedia diagram. As you can see, there's a lot here because you're covering not only the integer, you've got the original floating point, the accelerator, and depending on your system, you may not have all of these, or they may not be available. So anyway, that is an example of the problem. We'll discuss a little bit. I'm guessing people are generally familiar with this. The CPU is going to execute instructions. There are going to be intentional diversions from your code, such as system calls, which are fairly easy to know that you're happening. And then you have some external events. Now, these could be interrupts, exceptions, signals, or any other architecture event. So I think people were talking yesterday about things like x86 SMI impacting real time. These things will also impact into safety because some of them you cannot really see what's going on. We'll assume that the code has been verified and the code is correct as originally stated, and that it's loaded fine. And you see that at the moment, traditionally you'd have complete control over this sort of thing, but in a modern system you have a lot of work there. So again, I mean, we're not going to be able to show a complete list here, but we'll go over a few hardware and software faults and look at possible mitigations to avoid these. So what we're trying to do is to avoid something that could go wrong turning into a hazard, which has a specific meaning for us of something terrible is going to go wrong that will hurt people. We'll try and also talk about some of the current kernel features. I really have about an hour or two's content for these slides, so unfortunately we'll be going to be a bit quick over some of them. Now, unlike our previous presentation, which was very interesting, we're going to start with hardware is not perfect. Modern systems are complicated, so we're going to assume that something is going to go wrong at some point. Given that the x86 manual has about 4 pages worth of microcode for just the system call entry, that's sort of pointing to this is a issue of complexity. So our 2 failure cases we're going to show are either you have no entry or multiple entry when you need it. For things like interrupts, this is not a problem because they'll probably get serviced elsewhere, but if your system call doesn't work or happens multiple times, you may not know about it. These sort of mitigations, you're going to have to look at your user code verifying the action or some sort of sequence information. so there's going to be several, there's a number of things. Some of these are going to be useful anyway for other reasons. Now, the partial entry, is a bit of more of a problem because we don't really have any statistics about how the modern process will go wrong. However, there are some useful mitigations currently in the kernel which will make life a lot easier. So if we assume, say, that the partial entry is something like the processor fails to properly change modes, we'll probably either run into memory permissions, there's supervisor access controls, which are SMAP and SMAP under the x86. The KPTI, kernel page table stuff, being used for mitigating Spectre is also useful here because you have a much less entry. You have a very small target for entry, and the rest of the kernel is not mapped. It's quite interesting to note that there is very little data about partial failures, and we don't know if anything is being looked at on this. We'll have to have a look. So moving on now, software faults. Now, everybody would like to think that software is perfect. Okay. So we're going to skip data corruption. I think some of that has already been talked about. What we might be also next interested in, and I don't know if that was touched on in the last topic, is incorrect task switching or bad kernel code. Now, there's a little bit of background to this. When the kernel is entered from, say, an interrupt or system call, the entry wrapper code saves only the integer state on entry, because that's what the compiler is generally going to be using. And as a optimization point, it will only save stuff that it thinks it's not going to use when it decides that the task is actually going to be switched out. So this is the things like the floating point and other extended state only gets saved and restored at the point of the kernel's switch to. So this comes back to, firstly, could you make sure, is the state going to be preserved between these points properly? And in the case of incorrect kernel code, I've used bad kernel code here. It might not be just a thing. This could be use of non-integer registers without telling the kernel that is going to happen. So the kernel has no chance of saving, say, the accelerator states when your crypto code starts doing its RAID computations. Again, we've had a look through the kernel to see if these things are actually reported. It actually seems that at most of the time there's very little evidence in the current kernel Git that there are, say, any bugs like this. I believe that there was a couple in the past in the ARM kernel, but I think those have been fairly historic. So we now move on to looking at some mitigation strategies. First one we looked at was task isolation. However, really the problem here is that things like kernel threads, interrupts still run. Some of the interrupts can't be blocked because they're doing important functions. So really we could go into this in more depth, but really currently you can't isolate a task. Again, you can do some kernel checking. However, this isn't going to, we don't know if this will get you 100% coverage. And also some of the kernel sanitizers are fairly heavy. So what we've been working on is a kernel mitigation to try and detect the sort of errors we talked about with bad task switching. So we're using shadow state. So we're basically taking like the kernel's TCB and making our own copy of it. and updating that as necessary. We wrap all the syscall and other entry points to save the state on entry and then compare on exit. I mean, this is currently about 2,000 lines of C, and we'll discuss some of the impacts in the next slide. So going on to the issues and discussing some of the things we found doing this. Well, firstly, we have a significant overhead to kernel access, which is obviously why it doesn't get done by default. I mean, we're looking at doing a simple test. Simple benchmark we did with the get PID call. We looked at about 170% slower. Thank you. 170% slower for integer and 460% slower on the floating point SSE type case. Since we don't really want to be messing with the kernel entry code because that's quite a complex area filled with various problems like dragons and things, we can't cover 100% of the code. I don't know exactly what we do, but we don't cover the entry 64 code itself because that's assembly and difficult. That sort of thing also may come to the end, make us not difficult with the upstream acceptability. We think we could probably get most of our stuff up to the kernel, but we don't know. We would have to carefully think about how this would work. Again, since the slowdowns on system calls, who knows? It's very useful for the safety case, but who knows what else. A quick overview of the issues we found when testing. Obviously, messing with this sort of stuff causes kernel loops, and those can take time to reboot on real systems. So we also tended to use QEMU as a useful development tool, but we have a virtual versus real issue. QEMU has some differences with the real hardware. Things like segment registers just don't work the same, and sometimes it just crashes. Now, we might be able to use QEMU to produce like the CPU hardware and microcode type faults, but again, we don't have any information about how those generally occur. So, and hopefully now we're fairly well up to our conclusions. So I think the first thing, mitigations can impact performance, but in our view, we can turn those on and off for the safety tasks. It's difficult covering 100% of the failures. So maybe a hypervisor might be useful here or something else. Testing can be time consuming. Also, I think going forwards, this is a fairly large and complicated task space. Maybe we could also look at user space mitigations, possibly also looking at improved task isolation. I mean, could we get to a point where we could say we have a verified set of kernel functionality that we can just have running and make it down to that? I mean, there's a lot of, I think Jens is going to talk about some system call testing soon. And again, I think a lot is going to be, some people probably have a lot of very useful input in this. So with that, I think the last couple of slides are copyright and about both parties. So, and thank you very much for having me. I don't think we have a lot of time left for questions, unfortunately.
Yep. Thanks for keeping it into time. We're going to probably go on the break, but if people want to continue to chat a little bit, but they can do that. Certainly there's the chats here and also on the Rocket chat to continue the discussion. So feel free to ask questions there and we'll try to keep the discussion going. But with that, I guess we'll be probably going on to break and we'll be back we'll be starting again in 10 minutes and I'll put up a little poll so that we know when most of the people are there. And we'll restart when we see people back. Okay.
Right.
Thanks, everyone. Thank you very much, Ben, and thank you very much, Jens. Very good talk.
Yep.
Okay. We've got about 16 people who've clicked on the fact that they're back. We're getting ready to start. Let me go queue up for Jens and Nicholas as the next speakers. See if we get a few more polling results, seeing people are here.
Nicholas, you there?
Yep.
Excellent. Okay. Excuse me, and I'm going to just queue up your slides.
So I'll take the steering, right?
Yes,
on the slide.
please. Okay, yeah, it's just a second. I'm giving it to you right now. There we go. You are the presenter. You should be able to find your slides now and switch them over.
Yep. Working on it.
Great. Sorry, I just had to upload Alexander's in the break. Good. Excellent. Okay, we can see the slides. Go for it.
Okay, so just give the word. Should we start?
Yes, please.
Okay, Nicholas, go ahead.
Okay, so we will be looking at some of the aspects of testing of complex systems. We've been hearing some things about concerns about correctness within the Linux kernel, within the hardware. So this is really going to just look at a very small subspace of this problem domain. And this is focused on or originate from safety-related work or using Linux and safety-related systems. But essentially, I think it has a lot.
Please don't mute me because everyone's coming in through my channel right now between Jens and Nicholas, okay? So keep going now, Nicholas. They should hear you.
Okay.
Okay, Nicholas, we're on slide 2.
Thanks. So, as I said, our motivation for this work is related to safety-related use of Linux. That implies that we have to gain reasonable assurance about correctness, behavioral correctness, and certain properties of the development that we're looking at, because the claim of suitability of using Linux, of course, rests not only on code metrics and so on, but on a large set of properties that we have to assure for a specific Linux kernel or a specific constellation. Now, frequently one might find people looking at field data say, well, Linux is being used in 100 million systems worldwide, servers are running on it, so we should be able to harvest that data. Essentially, the problem is that there's a lot of different systems and we don't really have the necessary detail of this data. So even if it might be technically possible to get some level of assurance from the many operating systems out there, it's actually not that strong an argument. And essentially all safety-related standards will point you to analysis and testing, because that's the only way how you can get sufficiently contextualized understanding of your specific system. So analysis will very often focus on lifecycle related issues, requirements, design process, how are bugs discovered, fixed, how long do they survive. We have seen a lot of studies on bug life, time, on CVEs, how long they survive, and so on. And the second aspect is testing. The problem, of course, if you're testing in very complex systems, the question is always, do you have a complete, can you achieve completeness of testing? And if we look at something like the Linux kernel, then this question is not that easy to answer. And next slide, please. So that brings us to the actual problem statement of testing Linux. Because a traditional view is sort of software is deterministic and hardware is potentially random. Of course, if you can put your Linux machine into a totally defined state and then say make the next step, then it might seem deterministic. First of all, you don't have the ability anymore to put a complex multi-core system or a superscalar multi-core system into a defined state. And second of all, as soon as you have physical and even only logical concurrency in place, it's actually quite hard to say precisely what the next step will be. Needless to say that we have a whole bunch of asynchronous events from outside of the system, as well as asynchronous events from inside of the system. If you think of dynamic wait states inserted in bus transactions, if you think of probabilistic algorithms in cache replacement, and so on. So essentially, the system behaves non-deterministically, and for the question of the correctness of the system call, it's not really that relevant if it's now attributed to the hardware, to the software. We just attribute it to the interface into the kernel and what's coming back as not being deterministic. So if we just run our test cases and sort of say, well, memset, whatever, and then check was memset successfully executed, this will most likely work, because if it wouldn't normally work, Linux would not be in use. But in safety, we're interested in rare events. We're interested in finding the corner cases in the range of 10 to the minus 8, 10 to the minus 9. That means one failure in something like 125 years of continuous operation is what we are interested in here. So just because we ran a test case and it was successful, that doesn't mean that it will be correct in the future, because we know from the non-deterministic behavior of the kernel that there could be a very large set of different paths taken and different states involved, even if we perceive the identical behavior from the perspective of the user space application. And if we look at the user space application itself, we're just controlling the formal parameters. Like if I look at the open call here, path, flags, and mode, and I can evaluate if my file descriptor is reasonable or correct. But that doesn't tell me that the path that I took to get to this valid file descriptor was always the same, or actually always a correct path. So that's what we have to look at, how we can get some assurance of correctness under the assumption that we don't really know the internal state of the kernel. That brings me to the model. Next slide, please. A much simplified model, but I think it's sufficient for what we really want to do today, and that is sort of enter into a discussion, get some feedback from the kernel community about what we're looking at and how we are looking at it. So we have a user space call with its formal parameters. We just saw that before was an open. We do a transition into kernel space, and there we're executing a number of functions. And a lot of these functions, or most of these functions, are of course related to the functionality that I called upon, the open call or whatever. But inside of these functions, there's a lot of branching points that actually depend on the global kernel state. You can think of things like if need resced or an RCU state, or you could have a completion, and depending on some state of some kernel thread, the completion could put you in a wait state or on a wait queue, or if the kernel was fast enough, you might find that you call complete and the completion already is done, so you just continue on. And of course, locking is an obvious candidate where you can depart into the slow path and can have a considerable rare path being executed through the kernel. You can imagine that if you sort of look at it from a very theoretical point of view, if you try to follow the path through the kernel source code, and you would assume that all of the unlikely events, all the unlikely conditions, like hitting low watermarks on buffer cache and so on, are activated at this call, that could have a very, very large variability. And this is our problem. We want to get this picture from the formal parameters being passed from the user space call and the return value that we can directly observe, and we want to get a glimpse into the kernel internal behavior so that we can make a statement about were the potential detours or a variable path that were executed sufficiently covered so that we can make a global statement about the overall correctness of a system call in this case. That brings us to the next slide, a short outline on the testing approach. Now, one thing that has to be said is we're not trying to come up with a general statement of correctness of any of the system calls. We're trying to really say, in context of a specific use case, a specific set of assumptions of use, is this system call with these permitted sets of formal parameters sufficiently correct or sufficiently assessed with respect to its behavioral correctness. So we have this subset that we have from our use case and assumption of use. We encode a number of test cases. Now we take the target system. Again, this is valid and only for a specific architecture, for a specific system in the extreme case. And we execute this test repeated number of times. And while we are executing these tests, we are f-tracing our test case. And in the background, we have a number of permitted tasks, possible tasks executing related and unrelated functions. And by doing this, we hope to execute the hidden states of the kernel so that we are effectively using our repeated test case to sample these hidden states of the kernel. You have to imagine it a little bit like a urine. The kernel is roaming around its possible state space. We are injecting a system call with identical parameters every time, multiple times. And every time we do that, we run through code in every one of the branches in the code or in any one of the data structures that could be impacted by the global asynchronously modified hidden state of the kernel is then being sampled. And if we do this long enough, and we have a random background load, then at some point we should get close to complete coverage of the possible execution path. So then we take statistical methods to estimate the completeness of these possible paths. How good did we cover these paths? The overall setup is not that complicated to do. You can just imagine this rerunning relatively simple test cases multiple times in a loop and f-tracing them while you're executing more or less arbitrary background load. But now this brings us to the key question when we're interpreting this data. Next slide, please. The key question, and that's what we want to really ask you as kernel developers or people involved in a kernel, is a question of independence. Because if you imagine we have this open call, I just had it on a slide before, a single open call. And the question is now, if this sampling on the state space is reasonably independent of the local history of the task. So does the read is it dependent on the write that preceded it in the same user space task or not? That's really the key question that we have to answer, because it has an impact on the test cases that we have to execute to get a valid statement. Can we execute independent individual system calls, sort of call by call, or would we have to look at permutations of all possible combinations? So if the state space of the kernel is indeed sort of a homogeneous urn that we're sampling from, then basically background load will randomize this urn continuously. We can simply sample. If this is not the case, then we would have to change this test strategy. So currently our assumption is that we have this independence. If this is true, then this test strategy becomes manageable. And if it would be arguably incorrect, then that would be the point where we'd have to look at how to handle this or change our strategy. It brings us to the last slide, the actual point of this little presentation to get into this discussion. So this is basically the scenario that we have. We have this process A doing something, whatever, just have your open and a read. And this one task is being traced. And you have to imagine this task will be restarted many, many times in a loop. And we will collect these traces while we're running more or less large set of background tasks, executing arbitrary system calls. And these system calls that are running in the background are in no way synchronized with the calls or the entry into the kernel of our target task being traced. So this is not only these background tasks, it's of course all the asynchronous events that the kernel can offer, anything from peripherals to thermal interrupts to IPIs and whatnot, kernel threads, and anything that the kernel has to offer with respect to concurrent tasks is effectively asynchronous with respect to the trace task. But the question that we have to you is very simple. Well, it's actually not simple, but it's simple to formulate. Is it justified to consider open read in such a scenario as independent, or do you think we have to look at sequences of calls to be able to assess the potential path that calls can take within the Linux kernel? With that, let's see what we get.
Thank you, Nicholas. Are there questions to this? I think we have a couple of minutes.
Yeah, we've got 10 minutes left. So if there's people who've got questions, by all means, unmute your mics and turn on your cameras if you wish.
One important thing to note here is that when we say dependence or independence of calls, we of course do not mean a direct parameter dependence. That is, a read with a file descriptor that's invalid certainly isn't going to yield much of a result. Same corollary is true. That is, you must always call an open to obtain a valid file descriptor in order to do the read. So that's not what we mean. Clearly, it's going to fail if you don't have the proper preconditions. but the dependence focuses rather on the question of independence focuses on the question whether, for example, two reads in succession will influence each other, or read or write. Even if they do occur on the same file descriptor, they are not a prerequisite to each other. I hope that helps a little bit.
A simple example where you could maybe see, if you imagine that within the call path of reader, then I guess it's quite clear that there is no way we could deterministically from user space cause this lock to be uncontented every time that we call read. And the question is are there other dependent paths in the kernel where the preceding calls could cause such a dependency? With other words, if it take all possible execution paths of read, would the preceding call condition it in some way so that only a subset is accessible from then on?
I had a question about, so a project that does a similar sort of thing to this is one called Syzcaller. It comes out of Google, Syzkaller, and it generates random sequences of system calls and often in multiple threads runs them, finds a terrifying number of crashes. And I think the data from them would suggest that everything is non-independent. And there are lots of ways for these processes to interfere with each other. But I want to caution that it's late at night in my time zone and I'm struggling to follow the precise technical definitions of independence and non-independence. But I would say, yeah, you might want to look at that project as being relevant to the way you're thinking about this.
Okay, we know Syzcaller, and it's actually exactly the opposite what they are doing. Because what Syzcaller is trying to do is trying to take all the formal parameters of your open call and randomize those so that it is inducing all possible corner case at the level of the formal parameters. What we're doing is we're executing the open thousands of times with identical unchanged parameters, and we know these are correct. We can put this constraint on the shift-related task, only use open with this subset of valid parameters. The question is it possible that the overall unrelated execution of the system could put the internal path of the valid open call onto a sort of a path trajectory through the kernel so that it hits some untested corner case and blows up?
I see. I think the answer is still yes from Syzcaller, but I'll let other people who know better talk to it.
I would say the same. Probably depends on the system call too. But I can't imagine that it is completely independent on every system call for every combination of parameters. It would boggle my mind if it was.
Again, the combinations of parameters are not independent. That's not the claim.
Right, that's right. I misspoke. Yeah, but I would imagine there are things that happen in the system that would make it be independent. Depends on the system call. I mean, you look at ptrace or something like that, which is extraordinarily complicated, or something more complicated than just open and close.
I mean, clearly, as Nicholas already stated at the beginning, we're clearly only focusing on certain syscalls. Those syscalls that affect the state or read the state of another process directly, they are excluded because we don't want them to be used in a safety relevant application for those reasons, for precisely those reasons.
Let me restate the question in a slightly different way. If I show you the ftrace of my first read, and I tell you what this application was doing before the read. It is open, it is a stat, and I don't know what. And the background load of the system is just random load. Can you predict what the F trace of the next read will look like? Do you think you could predict with reasonable reliability, better than random, what the next read F trace output will look like?
That depends on caching and things like that. Oh, somebody just said that in the chat. So I don't think you could. No.
Yeah, that's actually my big concern with this. Is it seems incredibly fragile. You know, caching changes in you know, further kernel development work. It seems going to be very hard to distinguish between regressions and the normal course of kernel development. Even fixing a security bug might change the F-trace path. And a tool that is very noisy has a tendency to get ignored by developers because it takes a lot of time to evaluate false positives.
Absolutely. This is not a kernel development tool. This is really just an assurance tool. And we're not assuming any changes. We're not trying to compare a read from kernel 5.4 with a read from kernel 5.4.2. We're only trying to assess how complete was our test coverage of the read system call, in the sense, did we reasonably completely cover all possible paths in the kernel? And our hypothesis is, if you cannot predict the read from knowing what happened before the read in application A, or in process A, in my example here, then we would consider the paths basically independent, and then it is legitimate to use statistical methods to infer how many potential unobserved or untested paths of read still are in the kernel, or how corollary, how good is the coverage that we achieved. So I know this is a very specific problem, and it's definitely not a kernel developer's tool in the classical sense. It is very specific to high assurance or safety-related systems.
Yeah, I think you would have to restrict your background calls very carefully as well. So if you're doing a read and simultaneously there are other things operating on the file system, that's going to influence it. But if you set your processes to not touch that very broad I/O path, then that might be a restriction you would need to make.
Exactly the opposite is what we're doing. We want to exercise the maximum possible state space of the kernel,
Okay.
so that we get every possible path that this read could have if it collides with other reads,
Okay.
even on exactly the same file.
Okay.
So you have to think of it a little bit like you're walking through New York, and you have random traffic and random road construction going on, random from your perspective. How long do you have to walk through New York before you covered every possible path from A to B? That's sort of the question we're asking.
Right. So I
Even
think
if
you're...
the taxi driver the same direction, bring me to Fifth Avenue.
Yeah. But I think my misunderstanding has been that you're trying to optimize for the exact opposite thing of what I've been trying to optimize for. You want this to be as unpredictable as possible, and I'm trying to think of things that could make it unpredictable and remove them. And you want to find the things that make it unpredictable and hit all of them as much as you can.
That's largely the goal, right?
So essentially, this is a very coarse-grained code coverage tool. right? Because we can also use a code coverage tool to look at every single basic block, and people have done that before. This is doing it at the functional level.
I mean, that was going to be my other question, whether KCOV would be a better tool than ftrace. And I think KCOV would be a better tool than ftrace.
That's possible, but essentially that wouldn't really make much of a difference with respect to the key question. May we test system calls independently? Or do we have to look at permutations of system calls?
I see.
What?
I have to think about it more.
On that note, I'm afraid we're out of time for this part of the session, but thank you very much, Nicholas and Jens, for starting off a good discussion. And by all means, feel free to keep it going in the chats. There's also been a question asked: is there a Git repo for the work too? And I guess Lucas, you're up. So if Jens or Nicholas wants to answer about the Git repo question while Lucas is queuing up, we can do that.
Actually, we do have it in a Git repo. The tool for this, it was initially developed in the context of the SIL2 Linux project. I don't have it on the slide, which is a omission on my side. But if you go to sil2.osadl.org, you should actually be able to find it there. Or just send email to Jens or me. We can point you to where to find it.
I'll post a link to the chat.
Perfect. Thank you. And with that, our next speaker up is Lucas. So please continue. And thanks again.
Okay. So the acoustics is fine. Yeah. Okay. So what I wanted to talk about is a key question that you've been facing when looking at results from static analysis. One of the issues that we encountered is that we run the tools, we get the results, and we find thousands of findings. And the question always is, well, I'm probably not the first one encountering that, but what do I know from others that have been doing that already? And unfortunately, the truth is, it's quite difficult to figure this out, right? I mean, you can, of course, try to look at mailing lists, but there's no systematic way to obtain that information. So the core question that I want to discuss is there a better way doing it than we're doing it now, right? So can we, the kernel community, actually maintain the results that we get from static analysis tools collaboratively? And this really breaks down to the question, do we want to do that? And if we want to do that, how do we do that? Well, right, static analysis tools, just a few pointers. You can think about various different tools that we are using already in the kernel development. Even extended compiler warnings, right? Extor warn, but also then dedicated tools that we have developed around the kernel, so SPARS, Smatch, Coccinelle, even linters somehow would count for me as a static analysis tool. So CheckPatchBL, Coverity, ClangTidy, and so on. So you can assume any tool of your choice. The technical difficulty is actually going to be a little bit different, but the general question remains. And the reason for it is that you always hit this problem of false positives. Now, the problem is that false positives, everyone has a different understanding when I'm discussing it. So I'm not going to use that term. I'm going to suggest a little bit different terms. So there's a true tool finding, right? So the tool uses some heuristics and it finds an execution path that really could happen. and that would lead to an unintended behavior, right? So a bug. Then we have false tool findings. So it works on some kind of heuristics, but it actually describes something that would that can actually never happen and can never lead to a bug. Then you have a true tool-induced change. So a finding is reported by the static analysis tool, and it actually makes a developer creating a change, and that's accepted by a maintainer. Or it's a false tool-induced change, right? So you have a finding, and no matter what you would change in this code, the maintainer is going to reject that code, that change to the source code. And you can think about the first one being a false positive or the second one being a false positive. In the end, there's really no big difference, because the following workflow happens. You have a static analysis tool, and it reports a finding. It's either a true tool finding, and then you can just patch the control flow or the data flow in the source. So you make a change to the source code, and you get into you propose it to the mailing list, and it's either accepted by the maintainer so that it doesn't show up anymore, or it's not accepted by the maintainer and the tool continues to report. Or you have the situation that it's actually a false tool finding, and now you have the possibility to improve the tool. So you modify either the configuration or you modify the tool, and the tool doesn't report it anymore. Or you have no way of improving the tool, and then you can at least somehow add annotations in the source, and that annotation would silence the tool or let it know that it shouldn't report about it. And again, you're in the situation, the maintainer accepts that, or he doesn't accept that, and either if he accepts the annotation, the tool doesn't report anymore, and if he doesn't accept it, the tool will continue to report. And the conclusion of this workflow is, despite all reasonable efforts of improving your tool and adding annotations, you need to accept that at some point a maintainer is going to say, I'm not going to take the burden of this kind of change or this kind of churn, and the tool is going to continue to report. Or you're going to find out, okay, the tool just cannot be improved in such a way that it continues to report. And the unfortunate situation is that if you think about this workflow, the complete upper part can be handled individually and can be handled independently from each other, right? If you find a way to annotate the source, if you find a way to change the source code, if you find a way to improve the tool, all of those things will not show up for any further collaborative working with you. But if it continues to report, this will happen with every collaborator that works with this tool. Yes, so now the question is, of course, okay, we have this and have findings that will continue to be reported. So now is the question, is that actually a real problem in the kernel development? So I just ran sparse and Kernel, but I guess you can run other tools as well. And you'll find that we have thousands of warnings and errors in there. Now, from the discussions that I had with various tool developers or people using those tools, creating fixes, and discussion like that, and our own evaluations as well, we found out that most of those findings are actually, you can't really silence them, or the patches are not accepted. So you end up with a situation that we have thousands of findings, but none of them are really actionable. And the only way forward, as it seems, is that you would have to have a recording of all these findings and your argument why they cannot be accessible. So that's something that Corey also suggested. I mean, that's kind of the obvious way forward, but it especially becomes interesting because when you have a larger group of distributed tool users, you need to have a way to have this database maintained in a collaborative way. And the question is, of course, how could you do that organizationally and how could you do that technically? Yes. So again, it's not unique. Yes, I agree, Kevin. It's not unique to static analysis tools, but certainly with static analysis tools, these findings are let's say most prominent when they happen. And of course, having some kind of database would be really interesting in that regard. Okay, so yes, how could this solution look like? I'm just going to go through a few polls, and then I would actually open up the discussion. So yes, does static analysis tools actually deserve more attention within the kernel community? Okay. I'm just going to show the results. So it seems that there is actually quite some interest in that. And so the second question is really, what's the state of our community effort that we're driving? Maybe, yeah, that's the second question. So is the use and reporting of static analysis tools already a well-organized community effort, or is there some need to improvement? Okay, so yes, certainly improvement is asked for, and most of the people actually acknowledge that there are many people doing individual efforts. Okay, yeah, just two more questions, and then we'll open the general discussion. So yes, the question is, of course, well, so if there's interest in that area, the question would be who would be actually interested and who is actually already involved in that, and how would that work better in a collaborative setting? So we're seeing here that actually the most superior, the most frequent answer is actually that people are tracking these findings. That's surprising to me, actually. But we also see that the same amount of people actually have tried it once, gave up, or tried it once and did something, but seemed not to be tracking afterwards.
Do you mean in the kernel or just in general for all code?
In the kernel. I was meaning in the kernel, but
okay, that's what I thought.
Yeah.
That may confuse some people because I do a lot of static analysis.
Yeah. So let's go for the last poll, and then we'll open up the discussion. I saw that Alexander was already. Okay. So actually, yes, many people would actually go the extra mile. Many people would work with it if it works with the current workflows. So I guess, yes, with that, I would actually want to open the discussion on, yeah, what are good ideas to move this topic forward.
I feel like the talk tomorrow on common reporting in the CI track might be of interest here. I know some folks are working on something called KCIDB that I think they're trying to aggregate some reports like this, but I don't have the details.
Yeah, so I can give a little bit of context on that. So in the status of runtime testing and test suites like LTP and so on, the kernel CI project is working on ways of collecting test results from a few different CI projects, including 0 Day and some in the Red Hat CKI project, and then the stuff that kernelci.org is already doing today. So we're actually discussing kind of collaborating on that, how to collect results in a common way in a centralized database for that type of thing. And so we've also started looking at the difference between how runtime tests differ from static analysis, so on. And so we want to be able to do the same thing for static analysis, and even things like KUnit, which is kind of in between static analysis and kind of traditional runtime testing. So yeah, this is something we're discussing in the context of the kernel CI project, and there's a talk about it tomorrow, which will kind of set the stage for a BOF later in the week as well.
But to understand that correctly, you're just considering probably one report per kernel, right? You're not really pointing to a specific line in the source code where because the test doesn't really point you, okay, this line is the wrong one.
The runtime tests don't necessarily do that. There's more pass or fail, or they report some measurement or something. But static analysis will have different types of.
You would still have to present it in some way, right? I mean, it's not just building a database.
Right. I think how you present the data, I think it's probably important to try to separate out what's a common reporting format and separate out, is there necessarily line information like you would expect for static analysis of the source code versus unit test failure. You could argue that having a common reporting format for both would at least allow people to aggregate and then start building different ways of visualizing them. But from there, people building visualizations can focus on just kind of parsing a common shared format, which I think would go a long way.
There has been efforts on this in the past. The Herodotus tool was available during the 2.6 kernel for Kernel, which was actually doing something like what we're talking about now, recording the Kernel results and ability to mark false positives there so that it would not be reported the next time you run the tool. So such centralized databases for static code analysis is actually not that hard to do. The question is only how do you feed the database and who provides this centralized database, so that then you run your COTS attack or your sparse or whatever, and then you just download the current data from the database to weed out the false positives.
But I think there's a couple of issues you need to consider if you do that. One of them, and that's a topic that other commercial tools have run into as well that use an approach like this, namely is how do you match back up? Because if you change code, things become more problematic just to get the matches going. And the other problem is, okay, now I lost my thread.
Well, I'm wondering.
We actually looked at that for Kernel at least. Basically, what we do is we match the Kernel findings back to the commit, and then we looked at how long did that commit survive in the kernel. The average survival rate of the false positives, we did it around the 4.9 kernel set some time back. The average survival time of false positive was years. So once you're at the patch level or the commit level, it's not that hard to say nothing changed because a lot of tools have local context. For runtime tests, you're right, because for a runtime test, you can change something at the other end of the kernel, and that could invalidate your pass-fail. For a static code analysis, most of the time it will not invalidate the result.
Okay.
Yeah, so I think we're at the top of the time slot. Yeah, thanks for the suggestions. I think we should take that further, either in the chat or then in a hack room. Actually, I did have some experiments as well, and you find on the kind of continued slides the questions, right, that we probably would need to answer if we want to move this forward, right? I mean, where and how to store, how to collaborate, and so on. Things that you've already suggested, and I think Kernel CI could actually be a good way forward for that.
And maybe regrouping during the talks tomorrow that are relevant as well then.
Yeah.
Might be a good way of moving this forward. Thanks again, Lucas, for this. And I've turned over presenter now to Alexander. And so Alexander, if you want to unmute and then select your presentation.
Hello, do you hear me?
We do.
Oh, nice. And the presentation?
If you go to that plus at the very bottom of your screen.
Yes, I see.
You can go there, then you can go in and select your presentation and type in the circle and then hit confirm. Yep, you're up.
Yep. Excellent. My talk is called, first of all, hello everyone. My talk is called Following the Linux Kernel Defense Map. I'm Alexander Popov. I'm Linux kernel developer since 2013. And I'm security researcher at Positive Technologies, where I'm focused on Linux kernel vulnerability discovery, exploitation technique for those vulnerabilities, and developing the defensive technologies. The plan of the talk, we will follow the Linux kernel defense map, and then we will explore the kconfig harden check tool. I have a lot of things to tell, so I will try to run fast. Linux kernel security is a very complex area. There are vulnerability classes, exploitation techniques for those vulnerabilities, bug detection mechanisms, defense technologies. Some of them are in the Linux kernel mainline, some of them are out of tree for various reasons. There are commercial defenses, and there are some defenses which require special hardware. And all this stuff have complex relationships. All these items have complex relations. And when I started to learn this area, Linux kernel security, I understood that I really need a map for easier navigation. and I created the Linux kernel defense map. You can see the link to the project repository. I started this work in 2018, and I'm still improving and updating this map. The key concepts of the map, you can see them. I already mentioned that those are mainline and other kernel defenses, bug detection mechanisms, various vulnerability classes, and exploitation techniques. And each node, each link between nodes represents some kind of relationship, which doesn't always mean full mitigation. The details should be checked in the documentation. And this map doesn't cover cutting attack surface of the kernel. It is only about the kernel defense. The map is very big, so I will show it in several screens just to give the overview. So first, second, third, the most complex part, and the final part with the legend. So the map is very big, and I will show you some parts of this map to describe how to work with it. First part is about stack leak. It is a kernel security feature which was originally developed by Pax team, and it comes as commercial defense as part of jar security patch for Linux kernel. This feature erases the kernel thread stack at the end of the system call. So it cleans the information which was left on the kernel stack when the system call was handled. And so this defense technology can help to mitigate some information exposures from kernel space to user space, and also it mitigates some uninitialized memory usage. Moreover, this feature has additional checks against stack depth overflow. It is a special situation when the stack pointer goes out of the kernel stack memory region. It can be exploited for privilege escalation, for example. And this feature, this kernel defense, was upstreamed. I invested a lot of time into upstreaming this feature, and it was finally merged into kernel 4.20. And this map shows that stack leak is also available for the Linux kernel mainline. And here you can see that there is kernel memory sanitizer, which can detect information exposures and uninitialized memory usage. Another interesting part of the map, it is about control flow hijack exploitation techniques. Not vulnerabilities, but the ways how to use them for attacks. And here you can see that there are several types of control flow hijack techniques which are not mitigated for the mainline kernel at all. For example, Pax kern exec mitigates return to direct mapping, red to dir type of attack. And there is also the XP4 kernel patch, which is not mainlined. It is on hold currently because it gives very high performance penalty for the kernel. So red to dir attack is currently not mitigated at all. Another interesting thing is that control flow hijack is a very serious problem, and kernel needs to use hardware features to mitigate some kinds of such attacks. For example, there is read to user, return to user space attack which relies the main idea is to execute user space code from the kernel space when we have control flow hijack. And there is SMEP for x86. It stands for supervisor mode execution prevention, and similar feature for ARM, which is PXN, privileged execute never. Those hardware features with special support from the kernel allow to mitigate return to user space attack. But if we combine a return to user space attack with return-oriented programming and don't execute the code in the user space, SMEP can't catch it, and we need another type of mitigation. Another thing which I want to tell here on this part of the map is that those links which you see, as I mentioned, don't mean full mitigation, and they often mean really different things. For example, we have a really old return address override attack, and we have a link to this exploitation technique from stack protector kernel feature. It places a special cookie before the user's return address, and stack buffer overflow can't override the return address without overwriting the cookie. So that attack is detected and interrupted. But this link is not similar to, for example, pointer authentication on ARM64, which signs the return address. So even with arbitrary write, you can't change the address without knowing the secret for assigning it. So when you learn Linux kernel security in details, this map helps to navigate in the documentation and read more information. For example, if you are interested in return-oriented programming, you can look at the map and understand which features you can learn about and get the overview of return address programming mitigation. Now I want to tell about the map implementation. I have several requirements. First, I need to update the map regularly, at least every kernel release. And I want to develop it in text and not graphically, and use the version control system for this text. And moreover, I really don't want to place nodes and edges manually because it is a lot of effort. So I've chosen the dot language for this map. It is provided by awesome GraphViz package. So you write the graph, your map in text in this dot language, and run this simple command to generate the picture. Here you can see the example of the code for making this map. Here we define the type of the edge, and then describe that stackleak, the mainline version, has the link to Pax memory stackleak, which is original commercial version. Then we have connections between kernel memory sanitizer and the vulnerability classes which it can detect. And finally, we have the links between Pax memory stackleak and vulnerability classes which it tries to mitigate. Next slide. Strange. And you may ask, about knowledge sources which I used to develop this map. I, of course, used jar security documentation, Linux kernel security documentation, Linux kernel self-protection project, which is led by Case Cook, a Linux kernel mitigation checklist by Shaun C, and really nice talk, Trends, Challenge, and Shifts in Software Vulnerability Mitigation by Microsoft Security Response Center. And some other materials which I recommend you to look at. They are listed at the project documentation. And you may say, okay, nice map. And how about checking my kernel config for those defenses which this map shows? Yes, there are really plenty of Linux kernel hardening config options, and moreover, a lot of them are not enabled by the major Linux distros. And nobody likes checking kernel configs manually, so I decided to let the computers do their job and created the kconfig harden check tool for checking the security-related options in Linux kernel kconfig option list. I started that work in 2018 as well, and the project is growing and improving. I really like it. Here I want to show you the example output of this tool. The font is small, but I hope you can see. We simply give this tool our kernel configuration, kernel config file, and it detects the architecture. Currently, kconfig harden check supports x86-64, x86-32, ARM, and ARM64. It also detects the kernel version because some checks depend on the version of the kernel. Now it prints this table to you. First column is option name, the kernel kconfig option, which you can find in kernel configuration. Second one is desired value. So what value of this option is recommended for improving security? And the next column is very important. It is called decision. Here in this column, I show the origin of the recommendation. Who recommends to set this kernel option to this value? You can see that there are a lot of options which are recommended in default configuration, defconfig, and some of them are recommended by kernel self-protection project. And further, you will see other decisions. Next column is reason. Why it is, what particularly does it bring to security? Those options are for kernel self-protection. And final column shows the check result. It compares the desired value with the value in your kernel configuration and gives the result to you. Next part of the output. Yes, here you can see other authorities providing this recommendation. Another one is ClipOS. It is a very interesting project. It is the security hardened Linux distribution, GNU Linux distribution, and it has a very good wiki describing in details the reasons behind of their security recommendations. Some of the recommendations are marked as my. I work on putting those recommendations onto other projects, documentations, for example, for kernel self-protection project and ClipOS and some others. And then you can see that some options are marked as security policy. So it is not for kernel self-protection. It is for enforcing the security policy, which restricts the behavior of the user space. And then we see the options which can be used for cutting the attack surface of the kernel. There is a big list of options which decree, if they, for example, are enabled, they can make your kernel less secure or provide some debugging mechanisms which break the security boundaries. So here they are listed as options for cutting attack surface. And then on the next slide, you can see that a lot of such options, a lot of such recommendations come from kernel self-protection project, and some of them come from JAR security. I used last public JAR security patch and extracted the options which they mark as broken. They did it to show that those options have bad results for distribution security. Some of the recommendations are come from the kernel maintainers. So at the repository of the key-config harden check, we have some discussion, and some of the recommendations come from these discussions. Yes, cutting attack surface, and finally we have some recommendations for cutting attack surface from ClipOS, and some of them are from the lockdown. When lockdown patch set was not merged, I learned it and extracted the list of kernel functionality, which is required to be disabled by the lockdown patch set. And now I left it in the key-config harden check to show that this functionality can be bad for and used for changing the kernel image and breaking the secure boot and trusted boot chain. Finally, we have two options which influence the user space hardening, and at the end, the tool writes you the final results, how many options, how many checks were okay, and how many checks failed. Key-config harden check, as I already mentioned, has some knowledge sources. I want to show the origins of the recommendations and allow people decide for their case themselves. So the knowledge sources are kernel self-protection recommended settings, ClipOS kernel configuration, last public JAR security patch, security lockdown LSM patch set, and direct feedback from the maintainers. Now, about the project itself. It is GPL version 3. It is written in Python, and please don't cry if my code in Python looks like C code. I'm just a kernel developer who learns Python. The project has continuous integration, automatic functional tests, which provide code coverage 93%. It allows installation as a package, so it allows distribution via pip setup tools. And this project has nice contributors, and I'm very thankful for those people who support it and discuss various ideas at the project repository. And moreover, I know that this tool is used by several Linux distributions, and I even heard that one very big American security company used my tool for their security audits without giving credit to this tool. I got that information. It is funny, but it is obviously not good. Now, my conclusion, the main thing that I want to tell you. Linux kernel defense map helps to get the overview of Linux kernel security. And it is very useful for developing the threat model of your GNU Linux system. And when you developed this threat model, you can learn about kernel defenses, which can help you and cope against those threats. And the kconfig harden check tool, it is useful for controlling the security-related options in your kernel config. But please don't change your security-related options in your kernel without building and knowing your threat model, because it can be bad for performance, for security, and for functionality. It can break the functional requirements of your product. Yes, that is all. I wish you enjoy the conference, and I'm ready for questions.
We have about 5 minutes for questions if someone wants to unmute or ask.
And I will look at the chat. Maybe there are some questions there.
Yep, there's been a few. One thing I've got a question about specifically is for your kernel defense map. Have you been looking at, it's all sounds like it's done pretty much manually at this point in time, and I'm wondering, does it make sense to start to embed some key indicators to mine out of the kernel so you can automatically generate it going forward? I'm seeing this technique being used in some other places right now for putting special types of comments in, such that you, when things change, you can get them mined.
Do you mean the code?
Yeah,
so,
yeah. The code for the kernel defense map. I'm just wondering, it sounds like it's all being done manually right now. And I'm just wondering, is there ways that we could look at putting some comments in to the kernel around relevant sections so that we could mine it and then generate, such that if code moves out from under you, it's less, it's like, you know, you still have to manually check it, but also looking at generating it.
Actually, I think it is not dependent on the code, but it is more dependent on kernel configuration options, and also on the CWE, which I choose for this map. CWE, I see the question about that. It is common weakness enumeration. So it is big list of various bad situations in software which can bring your system down, and some of them have security implications. And I'm looking at this list, and I see a lot of items which mean the same or have some relations to each other. And if I just put all this CV into the map, automatically it will not look good, and it will be a big mess. And the same with kernel features related to security. If I automatically bring all the security related features, the links and connections will be very messy. So I'm trying to keep it visually useful. And at the same, and at the same time, I really like that working on this map brings some insights. So you can see that some bug classes can merge, or some kernel features can be combined together because they are trying to approach the same problem, but from different sides, for example.
Yeah, looks like Case has basically said he's not sure how much mapping external would have in putting in the kernel. But Corey's also asking in the chat, you know, how much of the maintenance can be automated. So you guys, you feel free to, unmute and start joining the discussion. Yeah, that's
so what I mean, right? Let's put the discussion in voice, not in the chat. But I mean, the CWE is a database. It's well maintained, and we can refer to a certain version. They're not going to change the numbers, and we can just add that as a link in the help text, and then you can just do a kind of sophisticated grep on the kconfig, and you have all that information as well.
Mm-hmm.
Of course, yes.
Yeah,
I don't know who's going to maintain that information, but we have that, right?
Yeah, I think it would be, it's helpful just as a general documentation idea. I think, and it can be seen very clearly in Alexander's map that some of the CWEs are really, really general, and some of the defenses are for really specific cases. Like, oh, it's a buffer overflow. Yeah, but is it a buffer flow in the page allocator? Is it a buffer overflow in the slab? Is it a buffer overflow in the slub implementation of the slab? Like, there's all these really tiny, subtle pieces that I think make this tricky to have. That said, it certainly would be nice to have CWE identifiers in the kconfig help text, which actually leads me to another question I'd asked, and this is, Alexander, and I think you're aware of it because there's an open bug in kconfig harden check and an open bug in the KSPP tracker that says, hey, how do we get a def config where we can select a subset of these things when building a kernel? And like, it would be interesting to get the full circle on that, where the kernel, you'd say, oh, I want this level of paranoia, go, and then that's sort of related to the same mappings that the kconfig harden check would do, is that there would actually be those different levels of protection available in the kernel by default.
Yes, that is a very interesting aspect. There were some efforts to bring these security-related recommendations into the mainline kernel, but it is very difficult. For example, let's take user namespaces. On one hand, user namespaces are good for process isolation. On another side, it is bad for kernel security, but because it brings a lot of new kernel functionality to unprivileged user. So it makes the kernel attack surface larger. So the same thing with extended PPF, eBPF. On one hand, we can write very precise rules for network filtering. At the same time, it brings this virtual machine with JIT into the kernel, which makes some security people nervous. So it is very difficult to enable the level of paranoia number 7, and we will have all this config options on special value. No, it is very difficult, and it is very different because we have different systems with different threat models, and microcontroller has different threat model from the cloud server or something like that. So that's why I just decided to create a separate tool, have fun with it, and give it to people to decide themselves depending on their requirements of their system.
Right, and I think that is the main thing. Is there's so many combinations here, it's difficult. The two ideas I'd had about it, but no one's really had the time to look at it, is you can do these sort of whatever paranoia levels we want as sort of the starting point. You say, well, I'm a system builder and I'm feeling very paranoid, so I'll pick this, and then you sort of work backwards from the config you've been given. And you say, oh, actually, I need that turned on. Oh, I need that turned off. But you start from a baseline that's like super paranoid, and that's a coverage way to do things. Another way is to look at it from sort of a use case idea, where you say, okay, well, the people who build embedded devices all tend to choose this subset of protections. The people who build servers tend to choose these selections. So picking one of those two ways, I think, would be an interesting approach to it. That said, it's a little awkward. Kconfig for these kinds of things is still a little bit awkward for doing these tiny snippets, but it does exist for like features. You start with defconfig and you say, actually, I also want KVM added. And you keep sort of building on pieces of it.
Mm-hmm.
Anyway, I think it would need somebody who's going to really spend some time on it and collect people's paranoia levels and try to find good, this is a good collection, that's a good collection, and spend the time working on it. But it's cool. I love being able to read the map because I get confused as well.
Another thing which I would like to bring is about performance. And for example, for stack leak, which is shown here, we have very different performance penalty for different types of workload. And I guess separating kernel defenses on system type is not enough, but we need something more to test the performance on some usual workflow for, let's say, database servers or web servers or something like that. So yeah, so performance evaluation is a very, very interesting aspect. And in kconfig hardening check, there is a link to a nice write-up about evaluating the performance penalty of each of those config options. I would really recommend you to see in the bottom of the README of kconfig hardening check.
Okay, thank you very much. And I'd highly encourage people to continue this discussion over in our chat session, and may possibly, people may want to group together in a breakout room at some point in time too to continue this. We're on a break. In fact, we've gone into the break, I'm afraid, a little bit much already. So I'm going to switch over to the break slide, and then we will pick up at the top of the hour with Shua and queuing up for that. So unfortunately, it's just a few minutes at this point now. So, but it was a good discussion. I didn't want to cut it off.
Thank you very much.
Thank you. Okay, well, we're pretty much back at the top of the hour. So, Shu, I've given you the presenter role. So if you want to queue up your talk and start, that would be great.
Okay.
You still have mute on, Shua, if you're speaking.
Yes. Yeah, just wanted to check if we have a quorum to start.
Well, there's about 86 people in the channel, and we
Okay.
said we started at the top of the hour, so
Okay, yeah, we'll go
going.
ahead. Yeah. Okay, so can everybody see my screen? I mean, the presentation part.
We can, and we can see the mouse moving too.
Okay.
All good.
I see. Yeah, that's a good test. I'll keep the mouse away from it. Okay, so I'm going to talk about the next kernel dependability. I have been thinking a lot about how we can bring general testing, quality assurance, all of the activities we do, security, safety, and then wrap them under a dependability. And then start to think about shifting from reacting to things versus a proactive. What can we do there? So, we do want our systems to be available, deterministic, reliable, and all of the other things that we want, resilient to attacks from remote as well as local attacks. Bottom line is, we really want our system to be dependable. Like, for example, we are doing this conference, and we want things to be, we need to be able to trust our systems. And then we also want to keep our data safe, and we want to be able to have access to our data, but at the same time, keep it secure. We have several obstacles in the way, right? So we saw from Alexander's talk a little while ago in terms of surface attacks, what kind of vulnerabilities we have, security vulnerabilities. And we deal with different kinds of overflows. These are all various obstacles, heap, integers, stack, the things that we introduce, bugs that we introduce in the kernel, in the code base. And we also do another thing that we go, okay, if printing this kernel address in the D messages is great because I can debug, but we do not think about aspect of, is that a information, are we leaking a privileged information into? This also true, not just D messages, it's also API and sysfs type interfaces, proc files. And then another thing we do is we don't always think about error and boundary checking, we do, but it's a human error. We miss doing that. And then sometimes we don't pay attention to out of bounds type access as we are coding. And memory leaks, use after freeze. And another thing we were able to, so in it, I noticed that as I was looking at the code, we end up not cleaning up in error paths properly, leaving memory and leaks in there. And uninitial is variable uses. We sometimes get data from user space, and this unsafe user data comes from, and we use it without in various in system calls, IRTLs, as well as networks and USB packets. So these are all the obstacles we have problems with in terms of this can lead to kernel panics, out of service systems, unauthorized access to data, and data leaks and losses. These are all the obstacles that stand in our way of having access to dependable infrastructure and systems. So let's see, moving from there, keeping all of these obstacles in mind, what do we usually do? We think, for the most part, we do reactive thinking in the sense that we find problems. We do regression testing. We do use fuzzers and run tests to find problems in the released code. And then we also we run dynamic and static analysis tools, and we also try to identify vulnerabilities by scanning for security vulnerabilities. We try to harden code paths, and we try to see if we can API. We fix a kernel API, and we use helpers so that we are not we are thinking kernel-wide when we find and fix these problems. The focus is, the bottom line is, the focus is finding and fixing problems in the released code. So can we do more? Let's talk about that. So shifting that reactiveness to a bit of a proactive thinking, investing in defensive designs, and also paying attention to common design and coding mistakes, like, for example, error paths, say. So can we get more coverage there? And then as we are writing code, can we do more there in terms of understanding the common mistakes that we make helps us design better. And so we are thinking about it at the back of our minds as we write code. And then also focus on detection, mitigation, and testing before code is released, as opposed to reacting after releasing the code. We have some tools available. We have CacheCheck, Sparse, Match. We use these in various bots, 0-day, and then reports, and then Dan Carpenter does reports, sending reports in. Several people look at them individually. So maintainers and developers react to those. So the question is, are there gaps in these tools? Do we need to enhance them and write new tools? And then as for the dynamic analysis comes in, we have syscaller, Trinity fuzzers, and then leaking memory. If you were to go through, check your system, run on your system, it can look at the system and tell you where things are, where you could be leaking. So we could also be doing these proactive things as we put a new feature in. Do we run and say, hey, am I leaking some privileged information in my API? Have I exposed it? Did I add that as a regression? And then if we don't have a test, can we write a test? And then keep using all of these tools during development and before code goes out. So these are all, I'll gloss over this one because I want to get to the next part, but there are lots of areas I find that these are problematic at times. And then these are all some of the bugs. If you look at the kernel the commit logs now, a lot of them kind of surround in this area in terms of where are we, some of the common problems that we see. And then we can do all of this stuff in terms of proactive design as before the code goes out. Sometimes we have just being mindful of the error and cleanup paths. And when we are in the error legs, we go out to release memory, or we're releasing all the memory. And then testing with this debug options for locking, debug options through locking. Can we do that? If we do that in the process, I think we do that. But I mean, keeping at the back of my mind, being conscious of that. And then also when we are adding new features and such, we could use these scanners that we have, config KCSAN, address sanitizer, and KMSAN. And I do use these in my testing at times. We can be diligent about that. Also connecting the dots, we again can we add hook these things, connecting the dots with the coverage we have, static coverage. Take a look at the recent work that was done with the KCOW, connecting that to the syscaller, doing effective testing. So we can do more of that. So we have regression tests. We actually save a lot of the sysbot reproducers. So we have all of those available. So we could be doing more testing as well before the code goes out. So I'm switching gears to talking about some of the CW, a common weakness. So if I look back and look at some of the things we talked about, the common problems sometimes we find, common mistakes we make, these do have show up as common weaknesses. Common software, as we are developing software, the mistakes we make. So in ELISA, we are looking at part of the ELISA and kernel dependability as a whole. We have been looking at the various common weakness enumerations. Yeah, let me just
going on here. I'm not sure where it's coming in from.
Let me just
going on here.
There is a lag too. Let me just check. Looks good on my end.
We're getting the loop back on your side, I think. There may be
Is it?
something that popped up back on your side, I think, until now. There may be something.
Is that better or no? Not at all. Okay. All right. So these are all coming from, there is a Lucas posted link to the definitions, common weakness enumerations, and I have some references at the bottom of the slide deck. So we started looking at various angles, various common areas, categories. So concurrency is one of the very crucial ones that we have. So we started taking a look at that, and then the work involves taking this common weakness enumeration categories, each of those categories, each of those common CWE itself, and then take that and see how to figure out what kind of detection mechanisms we have in the kernel, the static, dynamic analysis, and both, and then even the compile time hardening options that we have, and take that and see, do we have mitigations in the kernel that are already available? And if we have, look at those mitigations and then identify gaps, because we might have gaps in various areas of these things. Like, a Koch check might find some things, but do we have gaps in the scripts that we can enhance to figure out, give us better results when we run them? And the same thing with other static analysis tools. And the detection, for example, KC-SAN will do concurrency detection for this particular enumeration, CW, common weakness. So, and then we have mitigations. So identify all of those mitigations and identify gaps and see where we can go. We will have a better understanding of how we are doing in the kernel with respect to these common weaknesses. Take an example of this particular one, race condition enabling link following. It sounds vague, but the idea is that if this race condition between file and directory status, file and directory status checks and access time. This will result into time of check, time of use type race conditions. And then what kind of mitigations do we have available in the kernels that we can use, runtime mitigations? And this also is related to this particular common weakness is also related to discretionary access controls. This particular CWE, we do have mitigations in the sense that we can detect them with KC-SAN. The question mark in there is I haven't actually verified. So that's why that question mark is in there. I mean, I haven't done that. Mitigation wise, we do mitigate them with this particular race condition with SecCount, and we have a security module that can mitigate this. Moving on to the second one, that signal handle race conditions, that's of interesting one to look at. These are the race conditions in the signal handler itself in terms of using the signal handlers. We provide two kinds of mitigations in the kernel. Config signal FD, we have had this for a very long time, probably about 10 years or so. And a recent work done in terms of enabling signaling a process through PID-FD, which also includes eliminating PID wrap conditions. So this particular one, we know that we have mitigation. Is this enough? I do not know, but we do have it. So let's move on to the other interesting one. We have looked at, this is, we do keep fixing a lot of bugs in this area. So memory buffer errors. So this is a large list of errors in terms of large category with various errors related to memory itself, allocations, and then be buffer copying into buffers without checking the size, overflows, underflows, those kinds of situations. So all of these, we do a lot with this particular one. We have various detection mechanisms currently. We have this last one, buffer access with incorrect length value, GCC detection, W equal to 1 detection as well. We have several ways to detect this one. When we are also mitigating we go one step further than what CWE recommends in some places. Their recommendation is, yeah, let's use this and printf string copy, but we go one step further in the kernel that we actually go use sc and printf, which is good. So we are doing all of these things, and it's a matter of looking at understanding why we are doing that, or understanding we will be able to communicate from kernel perspective how we are mitigating, detecting common weaknesses that encounter. And people look at Go and CWE site and look at their common weaknesses. We'll have a map of what we are doing. So let's go look at there is more in this category. Memory buffer errors is quite huge. I haven't listed all of them actually. And so we have a pretty good detection and mitigation. This out-of-bounds read-write detection, we do that with static checkers, dynamic syscaller tests, and then using config KSOM. So another area I thought would be of interest to us is resource locking problems, because we do use a lot of locks in various areas, and then in the kernel. And then we do have, this is one area we do have a good coverage for in terms of how we detect them. And CACHA-check, for example, can detect a lot of looking at the detection angle, it can identify missing unlocks, double locks, and improper lock API usages, and holding locks in paths that require no lock holds, and so on. And then we also have kernel lock target tests that are available, locking API at boot time self-tests, and syscaller finds a lot of the problems, because the way syscaller goes about doing this is because of the randomness of the way it invokes system calls, and it tends to find a lot of those. So we're doing well in terms of in these areas that I looked at specifically. And then I gave these references. This is not the work I'm doing, and the rest of us at Lisa are doing is not limited to this. We're going systematically each category and identifying gaps. I highlighted the ones that I thought would be of interest to us, as these are the ones that we run into a lot. For dependability, for example, memory buffer type errors and resource locking problems and concurrency issues are the ones that could hamper our desire to have dependability. They have a bigger impact on dependability than probably some of the other things, other categories. So I want to leave time for discussion. That's one reason I wanted to kind of bring it all together. So my goal, as I'm looking at all of these things, I do want us to, I'm thinking that if we worked together, bringing it all together in terms of thinking more about common problems that we introduce in the code at the time before we release the code, and maybe identifying, put some of these practices into development, if possible, into our development process itself, and make it a habit to, because Lucas ran a poll during his talk. There is a lot of desire to use these tools more in the development. So it seems like we all have the desire to do it. because it helps us down the road, because we don't have to be reacting to problems that are coming in. So I think these are some of the things, takeaways, and then things to think about that I want to mention. Like, for example, we keep extending the write in new tools. Julia did presentation a little while ago talking about the new tool that she has for lists. And then hardening framework and code for identified gaps. And we have been doing that. PIDFD, SendSignal, and SecComp work that Case did recently, and kernel-wide thinking of how we can, when we find a problem, let's think more kernel-wide and say, when it's as needed and applicable, of course. And then masking, for example, kernel address pointer. We're not printing, we no longer print kernel addresses in the messages. We mask them. And then the continued work that we're doing with replacing SNPrintf and string things to address the overflow problems. So we are doing all of that. So let's see. That's my last slide. I want to generate some discussion and see what we can do going forward in this space. And then I'm going to share my research with what we are doing, CW research as well, as when we have it ready.
Quick question. You mentioned the saved syscaller proof of concept things. What's the reliability on those? Like the test frameworks that run those actually show them as triggering the vulnerabilities before they're fixed. How does that whole group of that collection, what does that look like?
I haven't given it much thought yet on that. That is another discussion. This is kind of discussion. So another idea I'm playing with is, would it be helpful for us when we identify a problem, for example, the work we are doing with string things, if we mentioned the CWE in our commit logs, would it help us? Would it help us scanning? If we looked at the commit log and looked up for CWEs that we are addressing, because we are doing a lot of work, because there is, to me, it is things like, they're all bugs, right? Whether it's a security issue or a dependability issue, safety issue, at the end of the day, they're all kernel bugs that we fix, and we do a lot of that. So for syscaller, we have the database that lists the fixed problems, but it is not in a way, I think, that it is hard to parse, I think. So for me, when I go look at it, I can't always tell. I look at it and then I have to do some work looking at all the fixed problems and figuring out what are fixed, which ones are fixed, and which release they are present. Are they still firing? So, I mean, probably that's your observation as well.
So yes, and also the question to me is actually, if we would add those CWE notations to the commits, we could actually find out what are kind of really the more critical ones. And then we could actually devise dedicated tools for that, right?
Right.
At the moment, it's just wild guessing. I mean, people are just like, yeah, that's my gut feeling, let's go.
Right.
I'm not sure it has any value marking with CVEs either, because you don't always know what you're fixing when it's being fixed.
Well, but so no, it's not a CVE. It's really a CWE in the sense of, okay, this was a typical buffer overflow. I don't know if it's a CVE. I'm not going to say it's severe or not. I'm just going to say it's a class of bug. That's all.
Right, and sometimes people fix things without even realizing there was a bug involved. So I mean,
sure. I mean, that's the problem of all statistics, right?
And just to give you a sense of scale. Remember, we have 4,000 developers a year. Training 4,000 developers to even understand what this is in order to properly mark their patches is going to be nigh impossible. We are barely lucky to get them to write a good changelog commit.
Right. So it's not something that we would require. If it's a low-hanging fruit, if somebody is familiar with it, and then if they can identify, that's more like it than requiring. Yes, Greg, it will be very difficult. Yeah, you're right. As getting commit logs right is in itself is a problematic.
One other thought, which is sort of the same, I beat this drum as well, is just getting testing right. One of the biggest problems I've encountered with most of the tree-wide changes and security mitigation additions and everything is people say, well, what's performance impact? And I say, well, here's what I measured with my thing. What do you care about? And they go, well, I don't know. Just we do network stuff. I'm like, okay, cool. What's your workflow? I go, I don't know. I'm like, okay, can you get a test in, please? Like getting tests into the self-test or the kernel. Like if you're going to go KUnit for behavioral tests or doing functional regression testing, but just writing the tests, writing workflows is super, super critical.
Right.
I need a lot more of that.
Looks like time is up.
And on that note, we're turning it over to Case anyhow. So I figure make it and then let you continue the discussion as you so desire, or go through and other things. I think it's going to be interesting. Just a sec.
So yeah, Case, take it away. You're going to talk about Yammer and SecComp anyway. So yeah, that'll be great. Thank you.
Okay, you should be able to pull your presentation up now. And it's up. Great.
Right.
Thank you. Go for it.
Yeah, so this is really a continuation of what Joao was already talking about, proactive dealing with security flaws. I tried to take a corner here on attack surface reduction and looking at that from sort of user space perspective. I had a couple quick notes just to sort of set the tone or direction, but I think a lot of folks that deal with security flaws all day can sometimes lose sight of the fact that security flaws are just bugs. Everything is a bug, and how it affects you is sort of the issue. There's no way for the upstream maintainers to objectively identify a severity for some flaw or bug, mostly because it's about reachability. Even if there's some extremely horrible flaw in TCP, which probably would affect most people, it boils down to there are some people who are not using network, and they don't care about that. So that's not an issue. They don't care if that gets fixed or not. The same goes for physical attacks. Is it on the USB stack? Well, if your machine's stuck in a secure colo, then you don't care if someone can walk up to your laptop and plug something in. Same thing for specific APIs in the kernel. Some scary I/O control has a flaw. Well, maybe SE Linux blocks attackers' access to it, and it again doesn't matter. And you get the same thing, coming back to kconfigs. If there's some problem with BPF, well, maybe the BPF syscall was compiled out, and nobody cares. So it's really, we're mostly just looking at this from bugs, and that's really reliability. A lot of the time, there's the three pieces of security, and a lot of attention tends to get given to confidentiality and integrity. Memory protection flaws and losing access to privileged information and stuff. But availability is a big deal of that as well. So if the flaw brings your entire machine down, you have data loss, that's a security problem as well. And what I hinted at a little bit was, sometimes a bug that gets fixed, the security implications aren't really understood for whatever audience that matters. Those things aren't understood for a year or more. So we have CVEs assigned for bugs that have been fixed in the stable kernel for a year and a half. And if people weren't running the stable kernel, then they are vulnerable to it. And another point that I sort of came up recently in some discussions is dealing with determinism. sometimes finding bugs is awful because you can't reproduce whatever is going on. You know, getting the system state into some correct position to trigger the bug is hard because maybe it's dealing with uninitialized memory or other things. So we've grown some features that both make bugs easier to find and easier to avoid, because suddenly uninitialized memory isn't uninitialized anymore, and it's not under the control of the random effects on the system or the concerted efforts of an attacker. If everything gets initialized at allocation time, a lot of bugs suddenly become unexploitable, or at the very least have a dependable failure mode, and they can be found more reliably. And then if you're debugging, of course, you probably want to do the same kind of thing GDB does with user space processes, and maybe turn off ASLR so you can always crash in the same place, things like that. So I think just thinking about determinism is another angle on considering bugs and dependability. But switching to the bulk of what I wanted to talk about is looking at attack surface reduction. If we can't reach a bug to begin with, we don't have to care about it. And there's the standard set of Linux security modules. Discretionary access control, that's stuff you can't get away from, as users and file permissions and Linux capabilities and things like that. That you can't really turn off, and everyone pretty much understands that really well. And on top of that are the mandatory access control systems. So having a good SELinux or AppArmor or whatever policy sort of narrows what any given process can reach. So you suddenly reduce the scope of your attack, and a running system has fewer states it can get into. As part of that, one of the pieces that is not entirely covered by Mac and DAC was ptrace. And I'll get into the addition of the YAML module, which sort of makes ptrace a little bit easier to think about. And I'll show some demos here. And the other one that a lot of people know about is setcomp, which is basically blocking the syscalls you don't expect to have access to, which means if anything goes wrong in that process, it can only use a narrow subset of the kernel, which means if there's a flaw somewhere in some piece that your program would not normally use, it stays unreachable, and it can't be hit on accident or on purpose. So quick overview on Yammer, you can turn on that way. It was the first stacked LSM in the sense that before LSMs were all or nothing. You either had SELinux or nothing, or you had AppArmor or nothing. It's sort of strange in the fact that the capability and the integrity systems were kind of bolted on sideways as well. So they were kind of stacked too, but Yammer was the first one that sort of declared itself as stacked. It changes the scope of p-tracing from the sort of default access control is any process with the same user ID can p-trace any other process with the same user ID, accepting dependability and some other things. And Yammer turns that around to sort of an ancestor tree to say you can muck around in ptrace for any child processes, but you can't leave your ancestry tree and go up or sideways, which gives you a little bit more, a narrower scope. And the thoughts on this were to basically expand the window, the time window needed for attackers to get a foothold, because there's, if you are already attacking a process, there's plenty of other ways to go to deal with it. But in theory, the hope would be that DAC or Mac would help with file-based things, but ptrace was sort of an open area. As a quick demo here, so if you don't have Yammer running, here's a sort of an ancestry tree of, init has started a bunch of things, and all of the green processes are owned by one user. Red is by another user, and the light blue is a sort of evil program that wants to attach to things and steal secrets out of some other program, like say your SSH keys or connections or whatever. And before, it the only thing that was happening was DAC would just check and say, oh yeah, your attack, the attack program matches Bash's user ID and the secret's user ID, so sure, you can attach that and steal everything you want. If you turn that on, then suddenly the ancestry tree is separate. You know, what started Bash there in the two instances have different trees of processes. This is one set of programs in a tree. This is another set of programs. So jumping from this branch to that branch, you can't do anymore because you do not share its ancestry tree. Now, if you're dealing with debugging, this isn't a problem. You've got GDB, you started on a program. GDB is the parent, it can ptrace the child, all as well. And dealing with crashing programs tends to be an awkward one because frequently the crash handlers are sort of siblings and not parents of the program that is crashing. So YAML grew the ability to declare who is allowed to ptrace them. So as the crashing program is crashing, it is able to communicate that the crash handler is who is allowed to ptrace it. So there's exceptions in YAML for doing sort of special things that go against a standard ancestry tree. Like this, you could declare it with a set ptracer. Anyway, moving on to seccomp, which is a little bit more well-known. This isn't really an LSM because it is not dealing with the high-level kernel objects. It is looking strictly at system calls. It depends on another feature called no new privs, which says, you know, once you have set the no new privs flag, you can't gain privileges through, you know, a setuid exec. So there's no chance of the old style attack that was sort of brought to attention through SendMail long ago, where you could cause SendMail to fail a setuid from its root user down to a lower privilege, and it would continue to run with the high privileges, but doing things as controlled by the unprivileged user. So seccomp avoids that by saying you can't gain additional stuff. Anyway, this is used pretty widely now. It's integrated pretty deeply into systemd, so you can specify all kinds of things. It's used in a lot of containers, and any program launchers tend to be heavy users of this. If you want to not muck with the code and add your own filters, or even use libseccomp, you can use other launchers like minijail that specifies a simple policy. Looking at how seccomp does its work internally, it's sort of looking at this information it gets at every syscall. It gets what system call number it is, what architecture you're running on. So for example, if you're running x86-64, you might be in compat mode, and you might get an i386 architecture instead. And the system calls map, the numbers map the different system calls depending on their architecture. An instruction pointer if you want it, and the actual numeric arguments to the system call. And the issue, due to how Linux is sort of designed right now, is that it is not safe for seccomp to actually dereference any pointers that are in the arguments. So it can't really read process memory safely right now. There's a whole talk on seccomp feature development tomorrow, where this is going to get discussed a little bit more. It's sort of an ongoing thread of discussion for seccomp. And when you do define a filter, you can handle a system call in various ways. You can allow it, you can log about it, you can kill off the thread, you can kill off the entire thread group. You can deliver a signal so that it can handle, the process can handle it itself somehow. You can pretend that this syscall happened and return an error number. You can generate ptrace events, and even now user notify, which uses a file descriptor for notification of events and handling what to do about how to process some of those. So a quick demo, if you want to just cat this file, run with minijail and specify what your security policy file, and it fails with SIG-abort. You're like, well, why? Look through the logs because minijail is going to be logging for you and say, okay, what is this? This permission denied. Okay, it's I didn't have sysadmin, or I didn't have no new privs set before attempting to use seccomp. So how do I set no new privs? Oh, okay, it's -n for minijail. Off we go. Let's try again. Okay, minijail -n, and we can cat this policy. Aha! Now that cat actually executes and finishes. Now we can actually see the contents of the policy, and it's just these system calls are allowed, and the other 300 and something syscalls are blocked. A pretty significant attack surface reduction. So, okay.
We're just seeing a blank screen and your mouse moving back and forth, so you may not have the window up.
I can see it just fine.
Yeah, I have no problem.
Okay, fine, it's me again. No worries. I'll shush up then.
Okay. So here we can see what, if we wanted to do something a little bit fancier, instead of just allowing these system calls, we could say, how about we have the openat system call return einval. And so we'll switch our policy for our cat, and suddenly we get this failure when cat tries to just open the file. And we can control the visibility of these sorts of things in returns. And finally, what if we change this from cat to ls? And of course it fails. And it's like, okay, why? I got a signal 31. Okay, that means it was refused, and let's copy over this policy and see what changes we need to make. So let's trace our minijail, see what happens, and see, oh, some IO control gets set. You go look it up and you say, okay, doing an IO control on standard out. Okay, fine, we'll allow that, but we can do something even fancier. Instead of allowing all IO controls ever, we can say, well, we'll allow an IO control on file descriptor 1, for example. And you just sort of keep this up, updating your policy until you've got coverage. This is a really basic example of how to build these sort of policies up. But as a result, everything is good. Anyway, that's it. It was just a crash course through a couple of ways to do attack surface reduction. Happy to take any questions or thoughts, or you can email me afterwards, or turn on your microphone here, or raise hands, or do whatever. I think I gained us back a little bit of time now. That is it from me.
Thanks, Case. Looks like you're getting compliments in the chat. Let's see if anyone wants to turn on their mic and ask some questions.
If anyone thinks of anything later, just let me know. Thanks a lot.
That sounds good. Well, then with that, thank you very much again to all of our presenters and for some of the interesting discussions that are starting. Feel free to join in on the Rocket Chat room after this conference is over, or after this mini-conf is over, and we will hopefully continue some discussions on these other sessions that are coming up in this week and the rest of the BOF. So if people have specific sessions that they recommend others go to, please feel free to put it into our chat and see if we can continue the discussions. Again, thanks again, everyone, for joining, and have a good afternoon. Bye-bye.